Tonight we descend beneath the clear waters of the Mediterranean, toward a discovery made in 1901 beside the small Greek island of Antikythera. You picture the sea first, darkening beneath you as sunlight weakens into blue silence. Far below, among broken amphorae, marble bodies, bronze objects, and rotting traces of an ancient ship, sponge divers encounter something almost impossible to recognize. It is not beautiful, it is not complete. It is a collection of greenish, corroded bronze fragments fused together by nearly 2,000 years beneath salt water. Yet those fragments will eventually force historians to reconsider what ancient technology could accomplish. Researchers working with major institutions, including teams associated with universities in Britain and the United States, have spent generations examining this object through photography, radiography, and modern scanning methods. Their work confirms that the fragments once belonged to an extraordinarily complicated mechanical device containing interlocking bronze gears. Nothing quite like it survives from the ancient Mediterranean world. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while the room around you becomes quieter, you might leave a comment with your location and your local time. There is something strangely fitting about people across the world listening together to a machine designed to measure the passage of time. You remain underwater in your imagination, where the seabed slopes beneath scattered cargo from a ship lost during the final centuries before the beginning of the Common Era. The divers who first explored the wreck are not searching for lost computers or forgotten technology. They are sponge fishermen, accustomed to difficult work and long descents in heavy equipment. What they find instead is a drowned collection of wealth. Marble statues lie pale beneath marine growth. Bronze figures appear through sediment. Pottery vessels rest where they settled when the ship broke apart. The entire place feels less like a museum than a room abandoned suddenly, with its possessions left exactly where disaster placed them. Then there are the bronze lumps. At first glance, they hardly invite attention. Corrosion disguises their shape, while mineral deposits conceal the delicate workmanship trapped inside. You might easily mistake them for broken fittings from the vessel. Yet as conservators begin cleaning and separating the pieces, tiny teeth appear along the edges of thin bronze wheels. More gears emerge, some are nested together, others overlap at precise angles. Their teeth have been carefully cut, suggesting a craftsman working with patience, measurement, and an intimate understanding of how motion passes from one wheel into another. That detail changes everything. Ancient Greek engineers certainly understood machines. Records confirm the existence of water clocks, lifting devices, pumps, theatrical mechanisms, surveying instruments, and complicated military equipment. Philosophers also wrote about celestial models, while mathematicians studied the movements of the sun, moon, planets, and stars. Yet the Antikythera fragments unite those worlds in an unsettling way. Here, mathematical astronomy does not remain written on papyrus or discussed beneath a shaded colonnade. It becomes machinery. Numbers become teeth. Cycles become rotating wheels. The heavens themselves are compressed into bronze. You can almost feel the rough surface beneath your fingertips. The surviving metal is brittle and uneven now. Nothing like the smooth object its maker once completed. Originally, the machine was probably enclosed within a wooden case, small enough to be transported yet sophisticated enough to require careful handling. Dials and pointers would have covered its faces. Inscriptions surrounded several displays, offering instructions or explanations. Turning a handle would set the interior gears moving together, each wheel influencing another according to carefully chosen numerical ratios. The quietest mystery begins there. The object does not merely show craftsmanship, it shows a system of thought. Someone has understood that astronomical cycles can be represented mechanically. Someone has calculated how many teeth particular gears require. Someone has designed a sequence precise enough for one rotation to stand for a month, another for a year, and others for much longer celestial rhythms. This requires more than metalworking skill. It demands cooperation between observational astronomy, mathematics, design, and workshop practice. For a moment, you hear only the imagined creak of an ancient ship. Perhaps the mechanism once travelled in a wooden chest beside expensive cargo, perhaps an educated passenger carried it as a prized possession. Perhaps it belonged to a wealthy patron fascinated by astronomy. Scholars continue debating its precise origin, destination, and ownership because the wreck refuses to provide simple answers. Several possible regions of manufacture have been proposed, and inscriptions preserve clues without revealing the name of the person who built it. The uncertainty is important. It reminds you that archaeology rarely delivers complete stories. More often, it gives fragments and asks whether patience can turn them into meaning. One curious possibility adds another layer. Ancient writers describe mechanical models of the heavens created by skilled Greek thinkers, including devices associated with celebrated mathematicians and inventors. Those descriptions once sounded almost literary, like elegant tales about clever philosophers. The Antikythera fragments make such accounts harder to dismiss. They do not prove every ancient story was accurate, but they demonstrate that complicated geared astronomical models genuinely existed. That realization settles slowly. You imagine a workshop somewhere in the ancient Greek world. Sunlight enters through a doorway. Bronze filings glitter on a bench. A craftsman leans over a thin metal plate while nearby, someone checks calculations scratched onto wax or papyrus. The work requires concentration. One misplaced tooth could disturb the motion. One poorly aligned axle might cause resistance. The finished machine must behave predictably because the sky itself is predictable, at least within the mathematical framework available to its designers. And yet almost nothing from that workshop survives. Wood decomposes, bronze is melted and reused, papyrus burns, tears, and disappears. Tools pass from one hand to another until their original purpose is forgotten. A machine made of valuable metal is especially vulnerable because later generations can transform it into coins, weapons, vessels, hinges, or ornaments. The sea, strangely enough, becomes the reason this particular object survives at all. The same water that destroys its casing also protects fragments from being recycled. There is gentle irony in that. The mechanism reaches the modern world because its ship fails to reach the ancient one. Had the voyage ended safely, the device might have been used for decades, repaired perhaps, inherited perhaps, and eventually dismantled. Instead, catastrophe places it beyond ordinary human reach. Salt water attacks the bronze, but the seabed keeps enough of it together for another age to discover. Researchers examining the wreck have therefore faced a peculiar situation. They are not simply studying one machine, they are studying the survivor of an unknown population. Was this device unique, created by one exceptional craftsman for one exceptional patron? Or was it one example of a technological tradition whose other machines vanished because bronze rarely survives intact? The evidence cannot yet settle that question. Archaeologists can describe what remains, while historians compare surviving texts, but the missing objects leave a silence around the mechanism. Your mind drifts again toward the divers. They could not have understood what rested inside those corroded pieces when the fragments first emerged from the sea. Even trained scholars required years to recognize their significance. The object revealed itself reluctantly. A gear here, an inscription there, a faint circular scale, a damaged plate hiding another wheel beneath it. Each observation made the machine stranger, not simpler. By the early years of study, investigators understood that these bronze fragments were no ordinary navigational instrument. They belonged to an astronomical calculating device, whose mechanical sophistication seemed centuries ahead of anything comparable that had survived. That phrase can be misleading. Of course, technology does not arrive from the future. The mechanism belongs entirely to its own world. The surprise comes from our incomplete picture of that world. That distinction matters. Perhaps ancient technology was never as simple as later ruins encouraged people to believe. Perhaps marble temples and handwritten philosophy have distracted attention from workshops where metal, mathematics, and practical skill met quietly. Perhaps what survives is only an uneven sample, favouring stone over wood, monuments over instruments, and famous texts over the anonymous knowledge of craftspeople. The sea gives no answer. It keeps the wreck in dim stillness, surrounded by the drifting sand and occasional currents. Yet from that silence comes a small group of bronze fragments, corroded almost beyond recognition, carrying the unmistakable teeth of gears. You look at them and begin to sense why this discovery remains so haunting. The mechanism does not merely reveal that ancient people could build something complicated, it suggests that an entire level of technical knowledge can exist, flourish, and then disappear so completely that later centuries scarcely remember it was possible. And the machine has only begun to speak. The sea around Antikythera is never entirely still. Even on a calm day, currents move quietly around the rocky island, slipping through channels where the Aegean and Ionian worlds seem to meet. You can imagine an ancient merchant vessel approaching these waters under a pale sky, its hull burdened with cargo gathered from wealthy ports, bronze statues, marble sculptures, glassware, pottery, coins, and luxury objects lie packed below deck. Somewhere among them rests a compact instrument of wood and bronze, carefully made, valuable, and probably incomprehensible to most people aboard. The vessel is travelling through a Mediterranean shaped by Roman power and Greek culture. By the 1st century before the Common Era, Roman elites are acquiring Greek art in enormous quantities. Victorious generals display sculptures and triumphs. Wealthy families decorate villas with imported works, and merchants move expensive objects westward through crowded sea routes. Archaeological evidence from the wreck suggests that the ship carried a rich collection of such goods, probably intended for buyers with considerable money and status. The vessel itself was large for its age. Studies of surviving timbers, cargo distribution, and the quantity of recovered objects suggest a substantial merchant ship capable of transporting heavy loads across long distances. You picture thick wooden planks flexing gently against the waves. Ropes creak, sailcloth snaps softly in shifting wind. Somewhere below, ceramic jars knock against wooden supports while bronze and marble remain tightly secured against sudden movement. A storm would change everything quickly. Antikythera lies near dangerous waters where winds can strengthen without much warning. The island offers steep coasts rather than welcoming harbours, and navigation in antiquity depends heavily on experience, visibility, stars, landmarks, and seasonal knowledge. Ancient sailors are skilled, but skill cannot command the weather. A damaged sail, an unexpected gust, or a mistake in darkness could drive a heavily laden vessel toward rocks with frightening speed. No surviving accountant describes the sinking. There is no captain's log and no passenger testimony. The wreck must be reconstructed from what the seabed preserves. Researchers continue to debate the exact sequence of events, including whether the ship struck the coast during severe weather or suffered another form of maritime disaster nearby. The evidence reveals the result more clearly than the cause. A valuable ship descends, cargo scatters, and human voices vanish from the scene. You hear the water closing over the timber, Heavy marble pieces tumble first, striking the slope below. Bronze objects settle among pottery and broken fittings. Wooden structures begin their slow collapse as marine organisms and time consume the vessel. Fine materials survive unevenly. Stone remains recognizable. Ceramic jars endure in fragments. Bronze develops thick corrosion. Wood disappears almost entirely except where unusual conditions allow traces to remain. This difference in survival matters more than it seems. Archaeology does not preserve ancient life fairly. Durable objects dominate the record simply because they resist destruction. Stone temples seem common because stone survives. Wooden machines appear rare because wood usually does not. Bronze tools vanish because metal is valuable enough to be melted down and reused. The ancient world you meet in museums is therefore not the complete world. It is the portion stubborn enough to survive. The wreck becomes an accidental archive. For roughly 2,000 years, the objects remain beyond ordinary reach. Fish pass through the debris, sand shifts across statues and pottery, minerals grow around metal surfaces, earthquakes may disturb the slope, fishing activity may alter parts of the site. Yet the depth protects enough material for the wreck to become one of the most important underwater archaeological discoveries ever investigated in the Mediterranean. The people who encounter it are not professional archaeologists. In 1900, sponge divers from the Greek island of Symi take shelter near Antikythera during difficult weather. Diving for sponges is dangerous work, performed in heavy suits with metal helmets and air supplied from the surface. A diver descends and notices what appears to be human bodies scattered below. The sight must have been deeply disturbing until the shapes resolve into ancient statues. Soon officials become involved. The Greek government supports a recovery operation, and divers are returned to the site. The work is exhausting and hazardous. They raise sculptures, pottery, bronze pieces, and other objects from a depth that place tremendous stress on the human body. Early diving technology offers little understanding of decompression sickness, and the expedition carries serious physical risks. Historical records confirm that divers suffered injuries, and one man died during the recovery campaign. The treasures arriving on land create immediate excitement. Marble figures emerge pale beneath deposits accumulated over centuries. Bronze statues reveal craftsmanship rarely preserved because bronze was so often recycled in antiquity. Objects from the wreck enter the National Archaeological Museum in Athens, where scholars begin sorting, conserving, and cataloguing the material. Among these spectacular finds sits something easy to overlook. It does not resemble a statue or precious vessel. It is compact, broken, crusted, and visually unimpressive. Yet the surrounding cargo provides an essential clue to its identity. The mechanism was not lying in isolation. It travelled within a commercial and cultural network connecting workshops, collectors, patrons, ports, and educated communities across the Mediterranean. This context transforms the machine from a mysterious object into a traveller's. You can picture its journey beginning in a workshop where metalworkers and astronomically educated designers cooperate. The finished instrument might then pass into the possession of a wealthy customer, teacher, scholar, or collector. It could be transported from one Greek centre to another, displayed in a private home, or shipped toward Italy as part of a larger transfer of valuable goods. One curious theory suggests that the mechanism may have been intended for a powerful Roman owner interested in Greek learning. This remains speculative. No inscription names a buyer, and no surviving document connects the device with a specific passenger. Yet the luxury cargo makes such possibilities reasonable enough to continue attracting discussion. Other interpretations move in different directions. Some scholars have examined calendar details and astronomical inscriptions for clues about where the mechanism may have been made or used. Proposed connections include regions of mainland Greece, islands, and cities associated with important mathematical traditions. The discussion remains open because inscriptions preserve cultural hints rather than a simple address. The ship itself therefore becomes part of a larger puzzle. A device this specialized would not travel casually. Its owner likely understood its value, even if every sailor aboard did not. It may have served educational, scientific, calendrical, or prestigious purposes. Perhaps someone demonstrated celestial cycles by turning its control while explaining the heavens to guests. Perhaps it belonged to a teacher who used mechanical motion to make difficult astronomy easier to understand. Perhaps it was admired partly because it was beautiful technology. A conversation piece for people wealthy enough to appreciate intellectual luxury. The Mediterranean smells of pitch, salt, oil, and damp rope in your imagination. A sailor crosses the deck carrying water. Another adjusts rigging. Someone below checks crates as the ship rises and falls gently. The mechanism remains packed away, silent and protected, its gears motionless during the voyage. There is a quiet irony in the cargo. The statues were meant to be seen. The ceramics were meant to be used. The luxury objects were meant to decorate rooms or signal status. The mechanism appears designed to reveal something less tangible, the mathematical order of time and sky. Yet when the ship sinks, all these intentions disappear together. Art, commerce, science, craftsmanship, and private ambition settle onto the same seabed. Centuries pass without witnesses. What survives does so by chance rather than importance. Many ancient masterpieces vanish while ordinary pots endure. Priceless texts disappear while broken roof tiles remain. A sophisticated instrument survives only because disaster removes it from the cycle of repair, resale, melting, and reuse that might otherwise have destroyed it. That possibility carries a slightly unsettling implication. The wreck may preserve not the extraordinary exception, but the extraordinary survivor. Countless ships crossed these waters carrying objects whose forms are now unknown. Workshops produced instruments that were never buried, never shipwrecked, and never protected from recycling. Their absence does not prove they never existed. The seabed offers only one preserved moment. You remain there in the dim Mediterranean, surrounded by cargo that never reached its destination. Marble eyes stare through sediment. Bronze limbs lie beneath marine growth. Broken jars rest quietly beside fragments of timber. Among them sits a machine designed to measure celestial order, preserved because human plans failed completely. The wreck does not explain the mechanism yet. It explains something just as important. Knowledge travels through fragile networks. It depends on ships, patrons, craftsmen, teachers, markets, and institutions. When those networks break, technology can vanish with surprising ease. You stand now not beside a shining scientific instrument, but beside a collection of damaged bronze pieces whose importance has not yet fully emerged. Their surfaces are rough, green, and split by corrosion. Some fragments seem almost geological, like stones altered by centuries beneath salt water. Then one detail catches the eye. Along a broken edge, tiny teeth appear in a regular sequence. They are too even to be accidental, too carefully diced to belong to a decorative object, and too numerous to ignore. The first scholars studying the fragments face a strange problem. Ancient Greece is already known for extraordinary achievements in mathematics, astronomy, architecture, and engineering. Yet the surviving material record does not offer many examples of compact machines filled with interlocking metal gears. This object therefore does not fit comfortably into the expected categories. It is neither sculpture nor weapon, neither vessel nor ordinary tool. Its internal structure suggests motion, calculation, and deliberate mechanical relationships. The teeth themselves tell a quiet story. Each gear must rotate against another with enough accuracy to transmit movement smoothly. If the spacing is poor, the wheels jam. If the teeth are badly shaped, the motion becomes irregular. A craftsman cutting bronze by hand must therefore maintain consistency across dozens of tiny projections. That task requires experience, patient measurement, and an understanding of how individual wheels behave as part of a larger system. You can almost hear the workshop's sound. A fine tool scrapes against the bronze. Metal dust settles on a wooden bench. A craftsman lifts the plate towards daylight and checks whether the teeth are evenly cut. There is no electric motor, no digital measuring device, and no factory producing standardized components. Every important adjustment depends on trained eyes, steady hands, and repeated testing. Records from the ancient Mediterranean confirm that toothed mechanical devices were not completely unknown. Greek writers describe automata, water-driven mechanisms, theatrical devices, and mechanical demonstrations. Engineers experimented with systems that converted one kind of motion into another, yet written descriptions rarely preserve enough detail to reveal exactly how sophisticated workshop practice became. The bronze fragments therefore provide something texts cannot. They preserve mechanical thinking in physical form. One wheel might seem simple. Several wheels working together are different. As researchers identify more toothed circles gear, they begin to see ratios hidden inside the machine. A small gear drives a larger gear. Another reverses the direction of rotation. A sequence transforms a single turn into slower or faster movement elsewhere in the device. The number of teeth matters because those counts encode relationships. The mechanism is not merely transferring motion, it is translating numbers into motion. That is the startling step. Suppose one gear represents a recurring celestial cycle. Its teeth allow another gear to turn at a mathematically related rate. With enough carefully chosen relationships, the machine can imitate patterns observed in the sky. Astronomy becomes something your hand can move. You turn one control and several pointers respond according to calculations built permanently into bronze. For historians of technology, this distinction is crucial. A gear used to lift weight performs a practical mechanical task. A gear chosen because its tooth count represents a numerical relationship performs a computational task. The object therefore occupies an unusual territory between instrument, model, calculator, and educational device. Modern scholars have compared the mechanism with descriptions of ancient mechanical traditions preserved in Greek and Roman literature. The surviving texts mention clever devices built to imitate celestial movement, but they often speak in broad terms. The fragments offer a harder kind of evidence. A tooth can be counted, a wheel can be measured, a damaged axle still reveals where another component once turned. Even corrosion becomes informative. When bronze parts remained pressed together during centuries underwater, mineral deposits sometimes preserve traces of surfaces that later separated. Investigators can study impressions, edges, holes, and faint circular patterns. A missing gear may leave evidence of its former position. A broken plate may reveal where an axle passed through it. Reconstruction becomes a kind of mechanical archaeology, where absence itself can carry information. One quirky feature of the object is its remarkable compactness. Ancient monumental engineering often impresses through size, with aqueducts, temples, harbour works, and siege machines dominating the imagination. Here the opposite happens. The sophistication is compressed. Large astronomical cycles are represented inside a device small enough to be handled by one person. That intimacy changes how you picture ancient technology. You no longer imagine only huge construction projects supervised by rulers or armies. You imagine private workshops where specialized makers build precision instruments for individual patrons. Such objects may have been rare, expensive, and fragile. They might circulate among scholars, teachers, collectors, and wealthy households rather than appearing in public spaces where archaeology is more likely to preserve them. This possibility remains debated. Some historians consider the mechanism evidence of a broader tradition of sophisticated geared instruments. Others warn against assuming that one surviving masterpiece proves common production. The disagreement is understandable because archaeology preserves an uneven sample. A single complex object may represent either a rare exception or the surviving edge of something once more widespread. You feel the cold metal in your imagination. A gear roughly the width of your palm does not appear mysterious by itself. Yet when dozens of components operate together, complexity grows rapidly. Each wheel must be positioned correctly, axles must remain aligned. The frame must hold the assembly firmly without creating too much friction. The outer displays must correspond with the hidden movements within. Mistakes would accumulate quickly. This means the maker probably did not improvise every stage. Some form of design process must have existed, whether drawn on a surface or calculated on wax tablets, recorded in notes, or transmitted through workshop teaching. Exact methods remain uncertain because no instruction manual for constructing this particular machine survives. Still, the completed object implies planning long before the first bronze plate was cut. That unseen planning may be one of the most important lost technologies of all. Tools can disappear, but methods disappear even faster. A workshop may possess unwritten tricks known only through apprenticeship. One craftsperson shows another how to mark equal divisions around a circle, how to correct a slightly uneven tooth, or how to fit an axle with minimal resistance. Such knowledge can vanish within a generation if the teaching chain breaks. Prestigious university research on ancient technology increasingly emphasizes these practical traditions alongside famous theoretical texts. Mathematics alone does not build machines. Skilled hands must interpret abstract ratios and translate them into physical parts. The Antikythera Mechanism demonstrates an unusually close partnership between thought and craft. You sense this partnership in every surviving tooth. The astronomer may understand a celestial period measured across many years. The mathematician may express that period as a numerical ratio. The metalworker must then transform that ratio into a pair of gears that actually rotate together. Three forms of knowledge meet inside one object, and none can succeed without the others. There is something gently unsettling about that unity. Modern people often divide intellectual work from manual work, placing theory in one category and craftsmanship in another. The mechanism suggests a setting where such divisions may have been more fluid in practice. Someone had to understand enough astronomy to know what movement mattered. Someone had to understand enough mathematics to calculate it. Someone had to understand bronze well enough to make the calculation turn. Perhaps these were different people. Perhaps one unusually educated craftsperson crossed several boundaries. The evidence cannot identify the arrangement with certainty. What remains certain is physical precision. The gears are not decorative symbols of knowledge. They work because their proportions correspond to chosen numerical cycles. This is why the object unsettles simple stories about ancient technology. The machine does not resemble a crude first attempt. It looks like the product of accumulated experience. That impression raises difficult questions. How many earlier devices were required before a maker could achieve this level of organization? How many failed prototypes taught workshops what not to do? How many simpler geared models once existed in wood, bronze, or other materials that never survived? The archaeological record remains quiet. You are left with fragments small enough to fit inside museum cases, yet large enough in implication to disturb an entire technological timeline. Tiny bronze teeth suggest skilled workshops, mathematical planning, astronomical knowledge, and mechanical traditions that appear only faintly elsewhere. And in those teeth, the ancient world begins to look less familiar. The bronze fragments begin to surrender their secrets only when scholars stop asking what the object looks like and start asking what lies inside it. Corrosion has fused plates together, crushed delicate surfaces, and hidden inscriptions beneath mineral growth. To the naked eye, many details are almost meaningless. Yet damaged metal can preserve information in peculiar ways, and every fracture offers another narrow entrance into the machine. You find yourself looking not at a complete object, but at a layered puzzle whose most important evidence remains trapped beneath surfaces no conservator can safely peel apart. Early investigators rely on careful observation, magnification, photography, and patient drawing. The challenge is immense because the fragments are fragile and irregular. Some inscriptions appear only as faint strokes, while others curve around circular scales that no longer survive intact. A single letter can change the interpretation of an entire dial. A single gear tooth can alter a proposed reconstruction. Nothing can be treated casually, because even tiny marks may carry numerical meaning. The first breakthrough comes from recognizing that the inscriptions are not decorative, they function as instructions, labels, and explanations. Ancient Greek lettering appears across plates that once formed part of the instrument's exterior. You can imagine a user leaning close to the case, reading small engraved lines while turning a control. The machine seems designed not merely to move, but to be interpreted. It expects an educated observer who understands that words and mechanical motion belong together. Some of these inscriptions describe astronomical cycles, others identify months, celestial phenomena, or the behavior of pointers. Their presence transforms the object from a silent mechanism into something closer to a scientific text written in metal. Instead of reading from top to bottom, the user reads while watching parts turn. Knowledge is distributed across gears, dials, and engraved instructions. This is unusual to feel almost modern. A prestigious tradition of modern research has examined these inscriptions using imaging techniques developed by teams connected with major universities and scientific institutions. Their work has revealed letters that earlier scholars could not see clearly. The process is less glamorous than the popular image of archaeology. There are no dramatic doors opening inside tombs. Instead, specialists spend months studying tiny variations in surface depth, shadow, and textures. The rewards are enormous. One method uses carefully controlled photography from many directions, allowing faint surface features to become more visible through changes in lighting. Another approach uses penetrating radiation to look through corrosion and examine hidden structures. These techniques let researchers study gears sealed inside fragments without physically dismantling them. What once seemed like solid masses begin to reveal interior layers, overlapping plates, and previously invisible inscriptions. You picture the machine becoming transparent without being touched. The sensation is almost ghostly. A gear hidden for centuries appears as a pale circular form inside the bronze. Teeth emerge one by one. An axle hole becomes visible, a line of text surfaces from beneath another layer. Preserved where no eye has looked since antiquity, the object seems to exist in several states at once. Broken on the outside, yet partially complete within its own mineralized memory. Radiographic studies confirm something especially important. The surviving fragments contain more gears than early researchers could identify by surface inspection alone. This discovery forces new reconstructions and sometimes destroys older ones. A proposed arrangement that once seemed elegant can become impossible when another wheel appears beneath a plate. Scholarship advances by correction as much as discovery. That can be strangely comforting. The mechanism does not reward certainty too quickly. Every confident theory must survive another scan, another inscription as another measurement. Scholars continue to debate the arrangement of missing components, especially where large portions of the original device have vanished. Some reconstructions fit the surviving evidence closely, while others depend more heavily on mathematical or astronomical expectations. The uncertainty is not a weakness, it is part of the evidence. One particularly curious detail is the density of the writing. The surviving letters are extremely small, suggesting that the machine was intended for close examination rather than public display at a distance. You imagine someone holding the case near a lamp, perhaps reading while another person turns a knob. This was not a temple inscription meant to impress a crowd. It was intimate knowledge, compressed into a portable object. The lettering also hints at craftsmanship beyond the gears themselves. Engraving tiny characters into bronze requires control and planning. The text must fit around circular displays, pointers, and mechanical openings. Whoever designed the inscriptions needs to understand both language and layout. The result resembles an instruction manual permanently attached to the machine. There is a gentle practicality to that choice. People forget things. Even educated users need reminders. A mechanism containing several cycles would be difficult to operate without labels. The inscriptions may have helped explain what a pointer represented, how a particular scale should be read, or what astronomical event corresponded with a position on a dial. The device therefore anticipates the problem of usability. That small fact brings the ancient maker closer. You can picture someone asking ordinary questions. Where should the label go? How much space does this word require? Will the user know which direction to turn the control? Can the scale be read in poor light? These are not abstract philosophical concerns, they are design problems. Historians sometimes speak of ancient science as though it existed mainly in books and lectures. The mechanism complicates that picture. Here, scientific knowledge has been shaped into an interface. A person does not merely contemplate astronomy, a person operates it. The inscription also provides clues about the cultural world of the device. Month names, festival references, and astronomical terminology can suggest connections with particular regions or traditions. Yet these clues are difficult to interpret because calendars differed across Greek communities. A familiar month name might appear in several places, and cultural exchange could carry terminology far from its original setting. Scholarly debate remains active for precisely this reason. Some researchers have proposed links with particular Greek regions based on the calendar system preserved on the mechanism. Others emphasize that linguistic and astronomical evidence can travel. A machine may be built in one place, adjusted in another, or designed for a customer living elsewhere. The surviving text narrows possibilities without providing a final birthplace. You smell lamp oil and warm bronze in your imagination. A craftsman bends over a plate, tracing letters with a sharp tool. Nearby lies a circular scale already divided into careful intervals. Work requires patience because one slip cannot be erased easily. The engraver must keep the spacing consistent while avoiding openings needed for axles and pointers. The machine becomes more human here. Its complexity is impressive, but its imperfections matter too. Some divisions are not perfectly uniform. Certain letters appear cramped. The object was made by hands, not by flawless industrial equipment. Its sophistication therefore cannot be dismissed as the result of hidden modern machinery. It is precisely ancient in its method, combining remarkable intellectual ambition with visible traces of manual production. There is also a fringe speculation that the inscriptions may conceal a kind of secret astronomical code known only to a small scholarly circle. Nothing in the evidence requires such a conclusion. The simpler explanation is that the text served practical and educational purposes. Still, the idea persists because the machine itself feels secretive to modern eyes, though its original users may have regarded it as simply difficult, expensive, and specialized. Difficulty often becomes mystery when context disappears. The hidden text gradually restores part of that lost context. It tells you that the mechanism was not built merely to impress with moving wheels. It was meant to communicate a structured understanding of celestial time. Every label helps connect motion with meaning. Every engraved word turns mechanical movement into interpretation. And this is where the corrosion becomes strangely useful. The damage that obscures the machine also preserves layers that might otherwise have been separated long ago. Plates fused together hold impressions, mineral deposits trap shapes, broken surfaces expose internal arrangements, destruction and preservation become inseparable, which is common in archaeology and still feels slightly paradoxical. You begin to understand why the object requires generations of study. No single scholar can simply open it and read the answer. Technology reveals what earlier eyes could not see. While new interpretations reshape old assumptions, the mechanism becomes clearer only through repeated acts of looking. The ancient words remain faint, but they endure. They survive as scratches beneath corrosion, small enough to miss and powerful enough to change our understanding of the machine. Through them, bronze stops being only material, becomes a voice, speaking quietly across centuries about calendars, stars, cycles, and the expectations of people who once believed that the heavens could be measured, described, and placed beneath the movement of a human hand. You turn the imagined handle slowly, and the heavens begin to move beneath your hand. This is the central wonder of the mechanism, not simply that it contains gears, but that those gears transform celestial cycles into something visible and mechanical. A movement of your fingers becomes a movement of time. Pointers travel across engraved scales, wheels rotate within the case, and patterns that unfold across months or years are reduced to a compact arrangement of bronze. The machine does not bring the stars closer, yet it gives their rhythms a physical form that can be touched. Ancient Greek astronomy had already developed sophisticated ways of describing the sky. Observers tracked the sun, moon, planets, and stars across repeating intervals. While mathematicians searched for relationships between those motions, records preserved through later authors show that Greek scholars inherited and adapted earlier astronomical knowledge from neighbouring civilizations. The Antikythera Mechanism turns that intellectual tradition into a portable model, allowing a user to explore celestial time without waiting for the actual sky to perform each cycle. Imagine the practical experience. You stand beside a table in a quiet room while afternoon light passes through shutters. The wooden case rests in front of you. Its front face carries circular scales and moving pointers. You place your fingers on a control and rotate it gently. The pointer representing the sun changes position. Another indicator follows the moon. Calendar information shifts around them, connecting ordinary human dates with astronomical motion. The effect would have been mesmerizing. Modern researchers often describe the device as an analog astronomical calculator. The phrase is useful because the machine does not calculate through written arithmetic while it operates. Instead, mechanical relationships embody the arithmetic in advance. The number of teeth on one gear determines how quickly another rotates. The designer has already placed the mathematics inside the machine, so the user experiences the result through movement. This is a remarkable form of compression. A celestial cycle lasting years can be represented by a gear turning slowly through a fraction of a revolution. A shorter cycle may appear through faster movement elsewhere. The physical size of the instrument remains modest, but these timescales represented within it become enormous. You are holding not merely an object, but a miniature architecture of time. Researchers associated with major universities and astronomical studies have emphasized how carefully chosen gear ratios reproduce known ancient cycles. The mechanism therefore reflects more than casual sky watching. It belongs to a tradition in which repeated observations are converted into numerical patterns. Once those patterns are known, a skilled designer can encode them into bronze. The machine makes prediction feel almost tactile. You can move the pointer to a date that has not yet arrived. You can reverse the motion towards a date already past. The heavens themselves do not move backward, of course, but the model allows time to be explored in either direction. That ability changes the relationship between observer and sky. Instead of waiting passively for celestial events, you can investigate their expected arrangement whenever you choose. There is a subtle intellectual shift here. A calendar tells you when days pass. A celestial model attempts to explain how larger cycles relate. The mechanism joins these functions, showing that human timekeeping and astronomical observation were deeply connected. Agricultural schedules, religious festivals, civic events, navigation, and ritual life all depended in some way upon recurring patterns in nature. The machine places those patterns into a single coordinated system. You hear the faint scrape of bronze against bronze. Real gears would not have moved silently. Even with careful fitting, there would have been friction, tiny vibrations, and perhaps a soft mechanical clicking as teeth engaged. The sound might have added to the experience, making cosmic order seem strangely material. Stars are distant and silent, but here their mathematical rhythms produce a small noise on a tabletop. One curious possibility is that the instrument may have served as a teaching device. A teacher could demonstrate how cycles relate without relying entirely on diagrams or verbal explanation. Students or patrons could watch a pointer move and see the connection between calendar dates and celestial positions. This possibility remains difficult to prove, but it fits the machine's combination of labels, displays, and interactive movement. Another possibility is Presto. A wealthy owner might value the mechanism not only for practical information, but also for what it represented. Possessing such an object could signal education, sophistication, and access to specialized craftsmanship. A guest entering a private study might see a compact machine capable of imitating the heavens and understand immediately that this household prize learning. The line between science and luxury may have been thin. Ancient scientific instruments often required skilled production and therefore could not have been ordinary possessions. Bronze, engraving, specialized labor, and mathematical expertise all carried costs. The mechanism may have been useful, beautiful, intellectually impressive, and socially prestigious at the same time. Modern categories sometimes separate these functions more sharply than ancient owners would have done. Scholars continue to debate how the front display was arranged because significant portions of the original structure are missing. Proposed reconstructions differ in details, especially concerning the representation of planetary motion. Some models suggest a rich display containing multiple celestial indicators. Others remain more cautious, emphasizing only what the surviving fragments securely support. The disagreement is valuable because it exposes the difference between what is known and what is inferred. You do not need every missing pointer to appreciate the underlying idea. The central achievement is already visible. The designer has created a mechanical bridge between mathematics and observation. Instead of writing that one celestial cycle corresponds numerically with another, the mechanism allows the relationship to unfold through gears. Knowledge moves. That movement carries philosophical weight. For ancient thinkers, the heavens often represented order, regularity, and intelligible structure. Planets might wander strangely, the moon might change shape, and eclipses might disturb ordinary experience. Yet careful observation revealed recurring patterns. A geared model makes those patterns visible in a particularly persuasive way. The universe appears not random, but structured enough to imitate mechanically. It is tempting to imagine that the machine gave its users a sense of mastery, yet perhaps wonder is the better word. The instrument does not control the sky. It merely demonstrates that human reasoning can recognize order within it. You turn a small handle, and the pointer responds according to a cycle observed across generations. The gesture is humble in scale and enormous in implication. There is also a fringe idea that such devices might have been used for astrological forecasting in addition to astronomical teaching. Ancient astronomy and astrology often occupied neighbouring intellectual territory, so the possibility cannot be dismissed completely. Still, the surviving mechanical and inscriptional evidence is strongest when interpreted through calendars, cycles, and astronomical prediction rather than personal horoscopes. The distinction matters because mystery can easily attract exaggeration. The mechanism is extraordinary without requiring secret powers. Its genuine sophistication is enough. It demonstrates that ancient craftspeople could build compact instruments whose movements embodied mathematical models of the sky. That fact alone changes the texture of the technological landscape. You rest your hand on the imagined case again. The surface is warm from the room, the bronze beneath it remains hidden, turning in precise relationships. Outside, the actual sun crosses the sky too slowly for your eyes to notice. Inside the machine, that movement becomes visible. Months can pass in moments. Years can turn beneath your fingers. A human hand briefly controls the pace of a miniature cosmos. Perhaps that was the deepest pleasure of using it. Not prediction alone, not calculation alone, not display alone. The machine offers a way to see time as structure, to feel that vast celestial rhythms can be gathered into one comprehensible object. The universe remains immense, distant, and mysterious. Yet for a few quiet moments its patterns fit inside a wooden case resting on a table. And there, beneath a turning hand, the sky becomes mechanical. The moon refuses to move with perfect simplicity. To an ancient observer, it crosses the sky with a rhythm that seems regular until careful measurement reveals something more complicated. Its apparent speed changes, its position shifts against the stars. Some months feel slightly different from others because the moon does not circle Earth in a perfectly uniform way. You can imagine generations of observers noticing these irregularities beneath clear Mediterranean skies, recording them patiently and searching for a pattern hidden within the wandering light. This is where the Antikythera Mechanism becomes unexpectedly subtle. Its makers were not satisfied with showing the moon as a pointer travelling at one steady rate. The surviving gearing indicates an attempt to reproduce variation in lunar motion through a clever, mechanical arrangement. That matters because representing simple repetition is one thing. Representing irregularity within repetition requires a deeper understanding of both astronomy and mechanics. Ancient astronomers knew that the moon's movement could not be described by one perfectly constant cycle. Mathematical models were developed to account for these changing speeds, and later, Greek astronomy would express such irregularities through combinations of circles and geometric relationships. The mechanism translates part of that mathematical thinking into physical motion. A small set of bronze components imitates a celestial body that seems to hurry and slow as it travels. You hear the soft scrape of metal in your imagination. One important arrangement appears to have used a pin moving within a slot. As the gears turned, this interaction altered the motion transmitted through the system. The result was not a perfectly even rotation, but a controlled variation that more closely resembled the observed behaviour of the moon. The design is elegant because the irregularity is not added randomly. It is built into the geometry of the mechanism itself. Researchers from major universities and scientific institutions have studied this feature because it reveals how advanced the designer's thinking had become. The mechanism is not merely counting equal intervals, it is mechanically approximating a changing astronomical rate. That is an important distinction, and it places the device within a sophisticated tradition of mathematical astronomy rather than simple calendrical display. For a moment, consider the intellectual leap required. A craftsman sees a circle of bronze, an astronomer sees a changing lunar motion, a mathematician sees a relationship that can be expressed geometrically. Somehow those three perspectives are combined into one working system. The resulting gear train becomes a bridge between observation and imitation, allowing a physical object to behave in a way that resembles the sky. There is something almost playful about it. The moon has always been visually familiar, yet its motion resists easy simplification. It grows and shrinks, appears earlier or later, and crosses different regions of the night sky. Ancient observers did not need modern instruments to notice that its behaviour was complex. Long records and careful comparison were enough to reveal recurring patterns, especially when astronomical knowledge was preserved across generations. The mechanism seems to encode part of that accumulated experience. The lunar pointer may also have displayed the moon's changing phase. Reconstruction suggests that a small rotating sphere or similar indicator could show the illuminated portion of the moon as it waxed and waned. If so, the user would not only see where the moon belonged within a larger cycle, but also how much of its face should appear bright. That feature would have been visually striking. You imagine the device resting on a table at dusk. Someone turns the control and a tiny lunar indicator changes appearance as the date advances. A dark portion grows across the sphere, then light returns. In a few moments, an entire month of phases passes beneath your eyes. Such a display is more than decoration. Lunar phases mattered deeply in ancient calendars because many systems organized months around the moon. Religious observances, civic schedules, and festival dates could depend on lunar reckoning. Understanding the moon therefore meant understanding part of the social structure of time. A council decree from the ancient Greek world might specify a date using a local month, while priests and officials depend on calendrical conventions shaped by lunar observation. The mechanism sits within that broader culture of reckoning, where celestial motion and public life were connected in practical ways. One quirky detail is that a user could theoretically move through lunar phases faster than nature ever allows, turn the control steadily, and days collapse into seconds. The moon that rises slowly across real nights becomes a tiny object obedient to your fingers. There is gentle absurdity in that image, as though the cosmos has agreed to become cooperative for once. Yet the machine does not truly simplify the moon, it preserves complication. That is the remarkable point. A simpler instrument could have shown one average lunar cycle and stopped there. Instead, the designer chooses to include variation. This suggests that accuracy mattered enough to justify additional mechanical complexity. The machine was not built merely to impress someone with spinning pointers. It was designed by people who cared about how closely physical motion matched astronomical theory. Scholars continue to debate how precisely the lunar system reflects particular ancient mathematical models. Some interpretations connect the gearing with well-known Greek approaches to lunar anomaly, while others caution that the surviving evidence does not reveal every conceptual step taken by the original designer. The mechanism provides the result more clearly than the reasoning process that produced it. That missing reasoning is fascinating. No notebook survives explaining why a specific gear count was chosen. No workshop diagram tells you how many prototypes failed. No teacher's commentary explains which astronomical source the designer trusted. The bronze provides a finished answer while hiding the path used to reach it. You can imagine that path only indirectly. Perhaps an astronomer explains a lunar cycle while drawing circles on a wax tablet. A mechanic listens, then proposes a way to reproduce the changing rate using rotating parts. They test the system. The motion is wrong. A pin sits too close to the center. A slot is reshaped. Another plate is cut. Gradually the model begins to behave more like the observed moon. it may have required several attempts. That possibility reminds you that sophisticated technology rarely appears fully formed. Behind every successful device lies a history of errors, discarded parts, revised measurements, and practical knowledge that seldom survives. The Antikythera Mechanism preserves the finished achievement but almost none of the experimental culture that made it possible. The silence around those experiments feels larger than the machine itself. Ancient written sources often celebrate famous thinkers, but workshops depend on many unnamed people. Someone casts the bronze, someone hammers the plates, someone engraves scales, someone files the teeth, someone checks alignment. The lunar gearing suggests collaboration at a level far more intimate than a surviving philosophical text can show. You sense the cold edge of the gear beneath your fingertip. Its teeth appear simple until you remember what they're doing. They're helping imitate the moon's uneven progress through the sky. A tiny piece of bronze becomes part of a model spanning hundreds of thousands of miles of real celestial distance. The scale difference is almost ridiculous, and yet the mathematics allows the imitation to work. Perhaps this is why the mechanism feels so modern to many viewers. It takes observation, converts it into mathematical relationships, and then builds those relationships into a machine. Yet nothing about that process belongs exclusively to modernity. The ancient world had its own traditions of abstraction somewhere, precision, and mechanical imagination. The moon reveals that clearly. It is not enough to know that the moon returns. You must notice that it wanders. You must measure the wandering. You must discover a repeating structure inside that irregularity. Then you must persuade bronze to reproduce it. That final step is where the mechanism becomes extraordinary. You look up at an imagined night sky. The real moon moves almost imperceptibly among the stars, indifferent to human schedules. On a table below, a smaller moon turns through its phases and variations at the pace of your hand. One belongs to the heavens, the other belongs to craftsmanship. Between them lies mathematics, and within that narrow space, ancient technology reaches a level of subtlety that still feels strangely unexpected. An eclipse begins quietly. The daylight remains ordinary for a while, and people continue their work beneath an apparently familiar sky. Then the sun starts to lose its shape. A dark edge enters the bright disk, slowly enough to seem unreal. Shadows sharpen. Birds may grow restless. The light takes on a strange quality that no ordinary cloud can imitate. To someone watching without explanation, the event can feel deeply unsettling. Yet ancient astronomers discovered that these moments were not entirely unpredictable. Hidden within long sequences of lunar motion, eclipses followed recurring patterns. The Antikythera Mechanism preserves evidence that its designers understood this recurrence well enough to build it into bronze. On the rear of the instrument, a spiral scale appears to have tracked a long eclipse cycle extending across many months. Instead of treating an eclipse as a sudden interruption of nature, the machine places it within an ordered sequence. Darkness becomes part of mathematics. This required patient observation across generations. A solar eclipse occurs when the moon passes between Earth and the sun in the right alignment. A lunar eclipse occurs when the moon enters Earth's shadow. Yet these alignments do not happen every month, because the moon's path is tilted relative to the apparent path of the sun. Most new moons pass slightly above or below the necessary line. Most full moons avoid Earth's shadow as well. The problem is therefore not simply counting months. Ancient astronomers had to recognize when several cycles return to approximately similar relationships. One especially important pattern repeats after a period of more than 18 years. Babylonian observers had documented eclipse sequences over the long spans of time, and Greek astronomers inherited a world in which such numerical regularities were already known and studied. The mechanism shows how that knowledge could be transformed into a practical display. You can imagine the rear face of the device beneath your fingertips. A long spiral scale winds inward, divided into many separate cells. Each cell corresponds to a particular month within the cycle. Some contain small markings indicating that an eclipse may occur during that interval. The pointer advances as the mechanism turns, carrying the user through years without requiring the sky itself to perform each event. The experience would have been strangely calm. Instead of waiting anxiously for darkness, you could examine the pattern beforehand. A particular month carries an eclipse indication, another does not. The machine does not guarantee that every observer in every location will witness the event, because visibility depends on geography and other factors. Yet it identifies periods when an eclipse becomes astronomically possible within the cycle encoded by its designers. That distinction reveals scientific discipline. The mechanism is not performing magic, it is applying recurrence. Researchers from major universities and scientific institutions have examined the surviving inscriptions and scale divisions, confirming that eclipse prediction formed a significant part of the machine's function. Their studies show that the rear dials were organized around known astronomical periods rather than arbitrary decoration. One of the most fascinating details is that the inscriptions appear to distinguish between solar and lunar eclipses. Small symbols associated with individual cells could identify the expected type of event. Additional information may have indicated the approximate time at which an eclipse was expected to occur. The bronze therefore carries a schedule of darkness. You picture an educated user studying the rear dial during a quiet evening. A lamp burns nearby, releasing the smell of oil into the room. The pointer rests over a marked cell. The user reads a tiny inscription and realizes that an eclipse belongs to this part of the cycle. The event may still inspire awe, but it no longer arrives without intellectual preparation. Knowledge changes fear without completely removing wonder. Ancient cultures interpreted eclipses in many ways. They could be associated with political danger, divine displeasure, military anxiety, or changes in fortune. Such interpretations varied across places and periods, and astronomy did not automatically erase them. A person could understand that eclipses recur mathematically, while still believing they carried symbolic meaning. Human beings are quite capable of holding both ideas at once. There is a quirky tension in this. A ruler might consult an omen while an astronomer calculates a recurring cycle, and neither activity necessarily cancels the other. The same eclipse can be a predictable celestial event and a troubling sign within a cultural system. The Antikythera Mechanism belongs to the mathematical side of that world, but it would have existed among people whose reactions to eclipses were not purely scientific. The machine itself cannot tell you what its owner believed. It can only show that someone considered eclipse recurrence important enough to encode mechanically. That decision implies a practical purpose. The user may have wanted to demonstrate astronomical cycles, prepare for future events, compare observations, or simply display the elegance of celestial regularity. A long cycle is especially suitable for machinery because human memory is unreliable. 18 years is long enough for ordinary recollection to become vague. A child who witnesses one eclipse may be an adult when a similar pattern returns. Written records preserve information across those intervals, but a mechanical model offers another solution. It stores the structure of the cycle in gear ratios and dial divisions. That is a form of memory. Not human memory, but material memory. Bronze remembers because its teeth cannot casually forget how many times they were cut. A gear with a chosen number of teeth repeats the same relationship every time it turns. A scale divided according to a long cycle preserves a numerical pattern even when the original astronomer is gone. The thought is almost comforting. A person dies, a teacher disappears, a workshop closes. Yet if the machine survives, part of the relationship they understood can remain embedded inside it. the mechanism becomes a container for knowledge that does not require continuous explanation to preserve its basic structure. Still, interpretation matters. Scholars debate exactly how users read certain eclipse inscriptions and how much precision the mechanism was intended to provide. Some markings are damaged or incomplete, and reconstructed meanings depend on comparisons between surviving letters, astronomical cycles, and mechanical layout. The broad eclipse function is well established, but finer details remain open to discussion. That uncertainty keeps the machine human. It was not an omniscient device. Its predictions depended on cycles, approximations, and the astronomical understanding available at the time. An eclipse might occur within the predicted period yet remain invisible from the user's location. The machine could forecast celestial possibility without providing the kind of geographical precision expected from modern eclipse maps. Yet for its age, the achievement remains remarkable. You're watching a culture convert one of the most emotionally powerful events in the sky into a repeating numerical system. Darkness is no longer simply an interruption. It has a place. It belongs to a sequence that can be studied, anticipated, and represented through machinery. Imagine what that realization does to the mind. The sun appears eternal each morning. The moon seems changeable but familiar. Then an eclipse suddenly alters one of them, reminding every observer that the sky can behave in frightening ways. To discover that such events repeat according to patterns is to find order inside apparent disorder. The mechanism makes that order visible. A pointer travels around a spiral, a marked cell approaches, an expected eclipse lies within the pattern. Nothing supernatural has been removed from the human imagination, but uncertainty has been reduced. The heavens become slightly less unpredictable. Perhaps this was one of astronomy's oldest comforts. You cannot prevent an eclipse, you cannot command the moon to move aside, but you can notice repetition, you can preserve observations, you can count months, you can compare generations of records. Eventually, you can build a machine that carries those recurring shadows quietly inside a wooden case. The room around you remains peaceful as you imagine the pointer moving. Outside, the real sky continues on its vast path. The sun shines. The moon travels invisibly through daylight or rises somewhere beyond the horizon. Their alignment belongs to distances far beyond human scale. Yet a carefully designed spiral can hold the rhythm of their meetings, and when the light finally fades, the machine is not surprised. The machine does not measure one kind of time, it measures several, and that is where its design becomes more revealing. You imagine standing before the rear dials while a pointer moves through months, years, festivals, and recurring celestial periods. These are not separate worlds for the ancient user. Agricultural time, civic time, sacred time, and astronomical time overlap constantly. A calendar tells you more than the date. It tells you when communities gather, when officials change, when ceremonies begin, and when the sky itself reaches expected positions. Ancient Greek communities did not share one perfectly uniform calendar. Different cities used different month names, different civic traditions, and different ways of organizing public life. This diversity makes the mechanism especially interesting because its designers had to choose a system that would make sense to a particular audience. The calendar scale was therefore not an abstract decoration. It connected the instrument to a lived social world shaped by local custom. You can imagine a user checking a date before a journey. The question might not simply be whether the moon is full, but whether a festival is approaching. A civic ceremony could interrupt business. Athletic gatherings could draw travellers from distant regions. Religious observances might shape when public activity slowed. Time was never just a number. One of the most fascinating features is the presence of a cycle associated with major athletic festivals. The mechanism appears to include a dial that marks the sequence of celebrated games held across the Greek world. These events followed recurring schedules, and their timing mattered far beyond sport. They were religious occasions, social gatherings, political meeting points, and opportunities for elites to display status. The dial makes human celebration part of the same machine that models celestial cycles. That choice tells you something important about ancient priorities. The designer did not build a device concerned only with distant stars. The mechanism links the heavens with the calendar of public life. A user could move through astronomical time while also seeing when important gatherings belonged within the wider sequence. Researchers connected with major universities have examined the surviving month names and festival references because these details help identify the cultural setting of the instrument. The evidence suggests connections with particular Greek calendrical traditions, though the exact geographical interpretation remains debated. Similar month names could appear in more than one region, and calendars were not always fixed in the tidy way modern schedules encourage you to imagine. Ancient calendars could require adjustment. Lunar months do not fit perfectly into the solar year, so communities needed methods to keep seasons and months from drifting too far apart. Additional months could be inserted according to established practices or administrative decisions. This created a practical problem that astronomy helped solve. If ceremonial dates depended on months while agriculture depended on seasons, the calendar had to keep both worlds reasonably aligned. The mechanism represents this challenge mechanically. Its calendar system reflects the effort to reconcile different cycles that do not divide neatly into one another. The moon does not conveniently arrange itself into a 12-month solar year. Nature offers several overlapping rhythms, and human beings must negotiate between them. That negotiation becomes visible in bronze. You picture the dial markings under warm lamplight. Month names curve around the scale. A pointer moves steadily as the internal gearing turns. Somewhere on the same instrument, another pointer marks a longer cycle. Another indicates a festival year. Each scale moves according to its own relationship, yet all of them are driven by one coordinated system. There is an almost bureaucratic elegance to it. Modern schedules often hide complexity behind printed calendars and digital clocks. The ancient mechanism exposes that complexity. It reminds you that timekeeping is a form of social organization. Someone decides where months begin, someone declares when festivals occur, someone observes where the seasons remain aligned. Astronomy, administration, and ritual become partners. A council decree proves how seriously ancient communities treated dates. Public decisions were recorded with references to magistrates, months, and civic calendars because chronology established legal and ceremonial order. A misplaced date could create confusion over obligations, offices, or sacred observances. The calendar was therefore part of government, not merely a private convenience. The mechanism may have helped educated users understand these relationships more clearly. One curious detail is that the athletic cycle associated with the device included more than the most famous games. The wider pattern of festivals reflects a networked Greek world in which communities recognize recurring gatherings across different regions. This suggests that the mechanism's cultural imagination extended beyond one city. You can almost hear distant crowds, not loudly, but as a soft memory carried through the machine. Sandals move over packed earth, vendors prepare food, priests organize ceremonies, athletes arrive with companions and supporters, wealthy visitors discuss politics, alliances, and trade. The festival calendar creates rhythms of movement across the Mediterranean just as celestial cycles create rhythms across the sky. The parallel is subtle but beautiful. Planets return, residences return, festivals return, offices rotate, families remember anniversaries, ships plan voyages according to weather, farmers recognize planting seasons. Human life becomes a collection of cycles nested inside larger cycles. The mechanism gathers these layers together. Scholars still debate the exact purpose of the festival dial. It may have been primarily informational, educational, or symbolic. The user could have consulted it to identify the year within an athletic sequence, or the dial may have served as another demonstration of how recurring human institutions fit within mathematical time. The machine does not explain its owner's habits. Perhaps it rested in a study and was turned during lessons. Perhaps it belonged to someone who travelled. Perhaps it served mostly as a prestigious object capable of displaying remarkable knowledge. Its combination of astronomical and social calendars allows several interpretations. A fringe idea occasionally appears that the device functions as a universal ancient planning machine, something approaching a complete scheduler for elite life. That goes too far. The surviving evidence supports specific calendrical and astronomical functions, not an all-purpose organizer. Still, the temptation is understandable because so many kinds of time meet within the case. You touch the imagined wooden frame. The surface feels smooth from use, a user turns the control and sees months advance. The festival pointer shifts, celestial cycles move elsewhere. Time is not presented as a straight line, but as a set of returning patterns. This cyclical view would have felt natural. Agricultural societies experience repetition constantly. Winter returns, harvest returns, and the moon fills and fades, and festivals recur. Political offices may rotate, children grow into adults and witness ceremonies they once watched from their parents' side. As time moves forward, yet much of life is understood through return. The mechanism makes return measurable. That may explain some of its quiet appeal. A future festival is not entirely unknown because it belongs to a sequence. A future phase of the moon is not entirely unknown because it belongs to a cycle. The user looks at the machine and sees that human events and celestial events can both be organized within patterns. There is comfort in recurring structure. Yet there is also fragility. Calendars survive only when communities continue to use them. Festival cycles remain meaningful only while institutions support them. A dial can preserve names long after the social world that gave those names meaning has disappeared. This is where the mechanism becomes almost melancholic. A month name engraved into bronze outlives the voices that once spoke it. A festival sequence remains visible after the crowds are gone. The machine preserves social time even when the society that created it has changed beyond recognition. You follow the pointer around the dial again. It passes through months once tied to ceremonies, markets, religious duties, and public expectations. It enters years marked by athletic gatherings, once crowded with travellers. The machine quietly insists that astronomy and ordinary life were never separate. The sky mattered because people built their schedules beneath it. And so the mechanism does not merely calculate the heavens, it calculates the human need to belong somewhere within them. Your attention shifts from the machine itself to all the older traditions that made such a machine possible. No civilization develops astronomy in isolation, and the Mediterranean world was threaded with routes along which merchants, scribes, soldiers, priests, and scholars carried ideas as naturally as they carried grain or bronze. Long before a craftsman shaped the mechanism's gears, observers in Mesopotamia had watched the heavens with extraordinary patience. Their records stretched across generations, preserving planetary appearances, lunar behaviour, and eclipse patterns with a discipline that would later influence Greek astronomical thought. The exchange was gradual rather than theatrical. Knowledge moved through conquest, translation, travel, and contact between courts and intellectual centres. You imagine clay tablets covered with careful signs, then papyrus sheets filled with geometric diagrams, then conversations in port cities where different traditions overlapped. One society contributes long observancy, another develops new mathematical models, another adapts those ideas to local calendars, instruments, or teaching methods. What emerges is not a single invention from nowhere, but a layered inheritance shaped by many hands. Babylonian astronomy provides one of the clearest foundations. Records confirm that Babylonian scholars tracked celestial events using long numerical series and recurring periods. Their ability to recognize regular patterns in lunar and planetary motion was remarkable, especially because it depended on disciplined observation over centuries. Greek astronomers later encountered this body of knowledge and adapted parts of it into their own mathematical traditions, combining numerical cycles with geometric models of the cosmos. That combination matters deeply. A Babylonian scholar might preserve a powerful numerical pattern without needing to explain it through a physical geometric model. Greek thinkers, by contrast, often sought to represent celestial motion through combinations of circles, spheres, and proportional relationships. The Antikythera Mechanism seems to sit at the meeting point of these approaches. It carries numerical cycles in its gear counts while presenting motion through a physical model. You can almost sense different intellectual worlds meeting inside the case. One tradition offers a long eclipse sequence, another offers geometric reasoning. A metalworker translates both into toothed wheels. The result is not Babylonian, Egyptian, or Greek in any simple sense. It is Greek in manufacture and cultural setting, yet intellectually connected to a much wider ancient network. Egypt also belonged to that network. Egyptian astronomers and priests developed sophisticated calendrical traditions, closely observing the year, seasonal change, and the rising of important stars. Their civil calendar became influential because of its regular structure, and Greek scholars living or studying in Egypt encountered a scientific environment shaped by centuries of local observation. Alexandria becomes especially important in this story. Founded in the Eastern Mediterranean world, the city grew into a major centre of scholarship, commerce, and scientific exchange. Its famous scholarly institutions gathered texts and intellectual traditions from many regions. Mathematicians, physicians, geographers, and astronomers worked in a setting where ideas from Greece, Egypt, Mesopotamia, and farther east could circulate with unusual intensity. Research from institutions such as Oxford University and Yale University has long emphasized how Hellenistic science developed within this broader environment of exchange. The familiar image of isolated Greek genius is therefore too simple. Innovation often appears where traditions meet, and the mechanism belongs to precisely such a world. You picture a scholar arriving in a harbour crowded with the languages. Sailors shout over cargo, incense mixes with tar, fish, and warm stone, merchants discuss weights and prices, a visitor carries a manuscript copied elsewhere, another brings astronomical tables learned from a teacher whose own sources came from another region. Knowledge travels quietly into baggage, memory, and conversation. The process is difficult to reconstruct because its transmission rarely leaves a perfect trail. A numerical cycle can appear in a Greek text without preserving the name of the Babylonian observer who first recognized it. A geometric model can be improved by several scholars before surviving in the work of one famous author. Technical craftsmen may adapt theoretical knowledge without leaving written explanations at all. This creates an open scholarly debate over how directly particular astronomical traditions influence the mechanism's design. Some researchers emphasize strong Babylonian roots in the numerical cycles encoded within it. Others focus on the Greek geometric tradition and argue that the machine represents a distinctly Hellenistic synthesis. Both approaches may capture part of the truth because technological objects often combine knowledge from several sources at once. There is also a curious fringe idea that lost Eastern traditions may have contained even more sophisticated mechanical astronomy than surviving evidence reveals. That possibility is impossible to confirm. No hidden archive of ancient geared computers has emerged from Mesopotamia or Egypt, yet the absence of surviving machines does not erase the possibility of technical experimentation whose materials were too fragile or valuable to endure. The more cautious conclusion is still fascinating enough. Ancient science was interconnected. You can trace this interconnectedness through the structure of the mechanism itself. Its astronomical cycles reflect observations too long to belong to one person's lifetime. Its mathematical relationships suggest theoretical traditions accumulated over generations. Its physical construction requires workshop skills refined through repeated practice. Each layer contains a different kind of inheritance. That is how complex technology usually grows. A brilliant inventor may contribute an important step, but the inventor never begins from nothing. Tools already exist. Measurement systems already exist. Mathematical language already exists. Patrons already understand what kinds of objects are valuable. Teachers have already passed down methods. Workshops already possess techniques for casting, cutting, engraving, and fitting metal. The mechanism therefore represents a civilization of accumulated competence. It also reveals how vulnerable that competence can be. Knowledge distributed across several cultures depends on continued contact. Trade routes must remain open. Scholars must travel. Texts must be copied. Institutions must survive. Craftsmen must find apprentices. Patrons must continue paying for difficult work, break enough of those connections, and the synthesis can weaken even if individual pieces remain. You imagine a numerical table separated from the workshop. The fellow knows how to turn it into gears. The table survives, but the machine does not. Elsewhere, a craftsman retains metalworking skill but loses access to specialized astronomy. The craft survives, but its scientific application fades. Complex traditions can fragment without any single dramatic moment of destruction. This is perhaps one of the mechanism's quietest lessons. Technology is not only an object, it is a network. The network includes observation, mathematics, materials, institutions, transportation, education, and demand. Remove enough threads, and the object stops being produced. Centuries later, historians may find one survivor and mistake the missing network for a mystery. The Mediterranean of the Hellenistic world was unusually suited to exchange. Kingdoms competed, ports prospered, and scholars moved among centres of learning. Political conflict was frequent, yet intellectual circulation remained active across large distances. This environment allowed knowledge to combine in ways that would have been harder within isolated communities. One famous example is the transmission of Babylonian astronomical periods into Greek scientific writing. These periods eventually appear within frameworks that use distinctly Greek geometrical concepts. The mechanism embodies the same tendency towards synthesis, though exactly which scholar or workshop made the crucial combination remains unknown. You can picture the process unfolding without a single dramatic breakthrough. A scribe copies a table, a teacher explains a cycle, a mathematician proposes a geometric interpretation, a mechanic notices that a ratio can be represented through toothed wheels, a patron funds a demonstration model, another craftsman improves the design. Decades pass, and fear and tradition become sophisticated enough to produce something like the Antikythera Mechanism. No one person needs to invent the entire world inside the case. This is why the machine feels larger than its maker. It contains traces of civilizations that never saw the finished object. Mesopotamian observation, Egyptian calendrical practice, Greek geometry, Mediterranean metallurgy, and Hellenistic craftsmanship all stand somewhere behind its bronze surfaces. Their contributions cannot always be separated cleanly, because cultural exchange rarely respects the tidy boundaries later historians prefer. Your mind drifts through those routes of transmission. A ship leaves one harbour carrying grain and manuscripts. Another arrives with merchants who know different star names. A scholar remembers a calculation learned abroad. A craftsman hears about an instrument built in another city. A Across generations, these small movements accumulate. Eventually, knowledge becomes machinery. And when you look at the mechanism, you're not seeing the achievement of one isolated culture. You're seeing an ancient conversation made physical, a conversation stretched across languages, cities, centuries, and skies that everyone shared. You enter an ancient workshop where the air smells of charcoal, warm metal, oil, and dust. Sunlight falls through a narrow opening and catches bronze filings scattered across a wooden bench. Somewhere nearby, a small furnace breathes with steady heat. Tools lie within reach, some simple enough to recognize, others shaped for specialized work. There is no factory, no standardized production line, and no printed manual resting beside the craftsman. Yet the object taking shape here demands accuracy so that would challenge even an experienced maker. The craftsman remains anonymous. No signature survives on the mechanism, no inscription gives the name of its designer, metalworker, or patron. This absence feels almost unfair because the object displays such extraordinary intelligence. Ancient literary culture often preserves the names of philosophers, generals, kings, and poets, while craftspeople disappear behind the things they made. The mechanism therefore offers a familiar historical imbalance. The work survives more clearly than the worker. You imagine the maker preparing bronze sheet. Bronze begins as an alloy that must be cast, hammered, shaped, and finished with care. Producing thin, reasonably flat plates requires control over heating and repeated working. The material must remain strong enough to support gears while thin enough to keep the instrument compact. Too brittle, and a component may crack during shaping. Too soft, and teeth may deform under repeated contact. Archaeological studies of ancient Mediterranean metalworking confirm that craftspeople possess sophisticated techniques for casting and finishing bronze. Workshops produce statues, vessels, tools, weapons, fittings, and precision objects long before this mechanism was assembled. The mystery lies not in whether ancient artisans could work bronze skillfully. The deeper question is how such familiar skills became specialized enough to create a dense mathematical machine. A gear begins as a circle. That sounds simple until you consider the required divisions. The maker must mark a precise number of teeth around the circumference. If the spacing gradually drifts, the final teeth will not meet correctly. If the circle is uneven, rotation may become irregular. The craftsman must therefore divide space carefully, using geometric methods, measuring tools, templates, or workshop practices that are mostly lost. You hear a fine cutting tool touch the metal. Each tooth takes shape gradually. The maker removes material, checks the spacing, then continues. A gear containing many teeth requires repetitive concentration. Fatigue becomes dangerous because a single serious error might ruin hours of work. Bronze cannot simply be restored once too much has been removed. The craftsman must know when to cut and when to stop. The workshop probably contains more mathematics than its humble appearance suggests. Circles are divided, centers are located, axles are aligned. Distances between gear centers must correspond closely enough for teeth to engage without excessive looseness. The plates supporting those axles require carefully placed holes. A small positional error in one component may affect several neighboring wheels. This is precision created without modern precision tools. Researchers at institutions such as Stanford University and Oxford University have examined ancient manufacturing methods more broadly, emphasizing the importance of skilled manual traditions in technological development. The Antikythera Mechanism fits this wider understanding. Its sophistication does not require modern machinery. It requires trained people who know their materials intimately and who possess practical techniques refined through repetition. That distinction is essential. Modern observers sometimes assume that an advanced object must come from an advanced factory system. Ancient production works differently. A highly skilled individual or small workshop can always achieve remarkable results through patience, specialization, and accumulated experience. The output may be limited, expensive, and difficult to reproduce, but it can still be extremely sophisticated. You picture a master teaching an apprentice. The lesson may not begin with theory. The apprentice learns how bronze feels under a file. He learns the sound of a tool cutting too deeply. He learns how to judge whether a plate has warped. He watches how the master marks a center point and checks alignment. Much of this knowledge may never be written down. That is one of the most important realities of craft history. Practical expertise often lives in bodies rather than books. A hand learns pressure, an eye learns proportion, an ear recognizes a bad fit by sound. Such knowledge passes through demonstration, correction, and years of repetition. If the apprenticeship chain ends, part of the technology ends with it. A surviving mathematical text cannot automatically recreate those skills. Instructions saying that 2 gears should engage do not teach a novice how to shape them properly. A diagram does not reveal the correct hardness of bronze or the best sequence of filing and fitting. The written theory and the workshop tradition depend on each other. The mechanism therefore suggests an environment where specialized craftsmanship had become highly developed. Was one person responsible for everything scholars cannot know? The designer may have been an astronomer who understood mechanics unusually well. Another possibility is collaboration between a mathematically trained planner and one or more specialist metalworkers. Large ancient projects often involved several kinds of expertise, so such cooperation would not be surprising. The evidence refuses to name the arrangement. This uncertainty has encouraged occasional fringe speculation about a secret guild of ancient engineers guarding advanced mechanical knowledge. There is no firm evidence for such an organization. Workshops certainly protected valuable skills, and families often transmitted crafts internally, but secrecy alone is not needed to explain the mechanism's rarity. Specialization is enough Imagine a workshop producing only a handful of such instruments during a generation. Each device requires many hours of skilled labor and access to knowledgeable customers. Demand may remain extremely small. Only wealthy patrons, scientific teachers, or institutions could justify the expense. The machines would then be rare even during their own time. This offers one possible explanation for their disappearance from archaeology. Rare objects made from recyclable metal face poor odds of survival. A damaged mechanism may be dismantled rather than preserved. Bronze plates become scrap, gears are melted, wooden cases decay. Within centuries, an entire technical tradition can leave almost nothing recognizable. You notice another challenge on the workbench. The craftsman must assemble the gears in layers. Some rotate closely beside others. Axles pass through supporting plates. Spacers prevent unwanted contact. The entire system must remain thin enough to fit inside its case while allowing many wheels to turn freely. Testing becomes unavoidable. The maker turns the drive slowly. A wheel catches. The assembly stops. He opens the mechanism and looks for the problem. Perhaps one tooth is too thick. Perhaps an axle sits slightly crooked. Perhaps 2 plates flex against each other. He adjusts the fault and tries again. This repeated testing is rarely visible in the finished artifact, yet it may represent the largest part of the labor. Successful machines conceal the frustrations that created them. Every smooth rotation may rest upon dozens of corrections. The same is true of the engraved scales. A dial must correspond accurately with the motion beneath it. The craftsman cannot simply decorate the surface and hope the pointer agrees. Divisions around the dial require mathematical planning. Labels must occupy usable spaces. Openings must allow axles to emerge without damaging inscriptions. Design and construction merge continuously. You begin to sense why the anonymous maker matters so much. The mechanism is not merely evidence of abstract Greek genius, it is evidence of hands. Someone held the tools, someone smelled the furnace smoke, someone became tired, made mistakes, corrected them, and returned to work. That person lived in an ordinary physical world. Perhaps he complained about the price of bronze, perhaps a customer demanded changes, perhaps an apprentice misplaced a tool, perhaps another commission waited unfinished while this difficult machine consumed far more time than expected. These details are unknowable, yet they remind you that extraordinary technology emerges from very ordinary human routines. An open scholarly debate continues over how specialized the manufacturing methods really were. Some researchers see evidence for a mature tradition of gear cutting and mechanical construction. Others caution that one masterpiece cannot reveal the scale of the entire industry. Both possibilities remain significant. If the mechanism came from a mature tradition, then many sophisticated objects have vanished. If it came from an unusually brilliant workshop, then ancient craftsmanship could still reach exceptional heights under the right conditions. You stand quietly beside the imagined bench. The gears are not yet hidden inside their case. They lie exposed beneath the sunlight, bright bronze rather than green corrosion. A craftsman lifts one between his fingers and checks the teeth along its edge. He does not know that his name will disappear. He does not know that the machine may outlive kingdoms, religions, languages, and entire systems of knowledge. He is simply trying to make the gear fit. And perhaps that ordinary concentration is the most human mystery of all. The name of Archimedes enters the story because ancient writers remembered him as more than a mathematician. They described a man fascinated by levers, balances, geometry, moving spheres, and machines capable of making abstract principles visible. You picture Syracuse in the 3rd century before the Common Era. Bright stone above a glittering harbour, workshops filled with tools, and scholars discussing the motion of the heavens somewhere within that intellectual world. The idea of constructing a mechanical cosmos no longer feels impossible. Ancient literary accounts describe devices attributed to Archimedes that represented celestial motion. Roman authors writing generations later mention spheres or models associated with him. Objects said to imitate the movements of the sun, moon, and stars. These descriptions are brief and sometimes shaped by admiration, so historians must treat them cautiously. Yet the existence of the Antikythera mechanism makes such reports much harder to dismiss as pure literary exaggeration. You imagine one of these lost models resting in a Roman house. A visitor watches as an owner turns a control and points out the apparent movement of celestial bodies. The device is not identical to the surviving mechanism, and no evidence proves direct descent from Archimedes. Still, the literary tradition suggests that geared or mechanically animated astronomical models belong to a wider family of ancient scientific objects. That possibility changes the scale of the mystery. If Archimedes or his intellectual descendants built celestial models, then the mechanism may not represent a sudden isolated miracle. It may belong to a lineage of experimentation extending across generations. One workshop solves a problem of rotation. Another improves a gear arrangement. A scholar proposes a more accurate astronomical ratio. Gradually, mechanical astronomy becomes sophisticated enough to produce compact instruments of extraordinary complexity. Records confirm that Archimedes lived during a period when Greek mathematics, engineering, and astronomy were deeply interconnected. His surviving works reveal intense interest in geometry, measurement, equilibrium, and mechanical principles. None of those texts provides a construction manual for the Antikythera mechanism, but they show that the intellectual environment needed for such a device certainly existed. You can feel the cold edge of possibility. Perhaps the surviving mechanism comes from a tradition influenced by thinkers working in places such as Syracuse, Rhodes, or Alexandria. Perhaps craftsmen move between centres, carrying practical knowledge in memory rather than written form. Perhaps astronomical model building became a specialized art known to only a small circle of scholars and patrons. Scholars continue to debate these connections because the evidence is indirect. Some historians emphasize the ancient literary references to mechanical celestial models and see them as support for a broader technological tradition. Others warn that famous names can attract speculation too easily, especially when the surviving object itself does not carry a maker's signature. That caution is necessary. Archimedes is such a powerful historical figure that almost any ingenious ancient machine can become attached to him in popular imagination. The mechanism does not need his authorship to be remarkable. Its value lies in what it physically demonstrates, not in whether a celebrated genius can be placed beside it. Still, the comparison is illuminating. A machine capable of representing celestial motion fits comfortably within the intellectual interests attributed to Hellenistic mathematicians. Theories of circles, ratios, and planetary movement could inspire physical models. A workshop capable of precision metalwork could then translate those models into bronze. You imagine a scholar drawing concentric circles on wax. He marks one cycle, then another. A craftsman studies the diagram and asks how the motions might be combined mechanically. The scholar answers with proportions. The craftsman responds with questions about space, friction, and materials. The conversation becomes practical very quickly. This is where famous theory meets anonymous skill. Ancient histories often preserve the theorist and lose the technician. A philosopher's says name may survive because students copied his works, while the craftsman who made his demonstrations disappears entirely. The mechanism reminds you that scientific achievement often depends on people whose names never enter literature. One quirky possibility is that sophisticated celestial models may have been used almost as intellectual entertainment among wealthy elites. A dinner guest could watch a mechanical sky move while discussing philosophy, mathematics, or fate. This sounds indulgent, but elite households in the ancient Mediterranean often displayed unusual objects that combined education and prestige. Such an instrument would be difficult to forget. Imagine the room growing quiet as the model turns. Lamps flicker against bronze surfaces. A pointer moves across a dial. Someone explains that the moon is not wandering randomly but following a measurable cycle. Another guest asks whether the planets can be represented too. The device becomes a conversation in motion. Major university scholarship on an ancient science has increasingly emphasized that demonstrations, instruments, and models could play important roles in teaching and persuasion. A mechanical model makes an argument visible. Instead of saying that celestial motions can be reduced to mathematical relationships, the device performs that claim in front of you. That performance carries authority. A person watching several pointers move in coordinated patterns might experience mathematics not as dry abstraction, but as something almost magical. Yet the magic comes from rational construction. The machine persuades precisely because its movements are predictable. This may help explain why ancient writers remembered mechanical spheres with such fascination. They were intellectually theatrical objects. The term theatrical does not make them unserious. Ancient science often relied on visual demonstration, geometric proofs, astronomical diagrams, hydraulic devices, and mechanical models could all make difficult ideas easier to grasp. A moving cosmos enclosed within a small instrument would have been especially memorable. There is a fringe claim that Archimedes possessed technological knowledge far beyond anything later civilizations recovered. That interpretation goes beyond the evidence. Ancient accounts praise his ingenuity, but praise is not proof of hidden industrial science. The stronger conclusion is more modest and more interesting. Hellenistic scholars and craftsmen were capable of combining mathematics and mechanics at a level that surviving artifacts only partially reveal. The distinction matters because lost technology does not require secret knowledge. It requires fragile knowledge. Knowledge est power. A specialized device may depend on several people who understand different parts of the process. If the astronomer dies, the mathematical model may become harder to reproduce. If the workshop closes, the gear-cutting tradition may weaken. If patrons lose interest, expensive instruments stop being commissioned. Nothing dramatic needs to happen. A technology can disappear through neglect. You picture a workshop where an old craftsman has no apprentice willing to continue the trade. Perhaps simpler commissions pay better. Perhaps political instability reduces wealthy patronage. Perhaps the astronomical models are admired but considered unnecessary luxuries. The final instruments leave the workshop one by one. Then no more are made. This possibility helps explain why literary references and physical evidence can become disconnected. Texts may remember extraordinary devices long after the workshops that produced them vanish. Later readers encounter descriptions but cannot inspect the machines themselves. Over time, memory becomes legend. The Antikythera Mechanism reverses that process because the physical object survives while the full literary context does not. You have the machine, but not the workshop record. You can count gears, but not customers. You can read fragments of inscriptions, but not the correspondence between designer and patron. The object therefore sits between history and silence. Archimedes becomes relevant not as a convenient answer, but as evidence that mechanical astronomy belonged within the imaginative range of ancient science. His reputation for celestial models suggests that the Antikythera mechanism may have had intellectual relatives now lost. How many? No one knows. Perhaps only a few highly specialized devices ever existed. Perhaps dozens circulated among wealthy scholars and collectors. Perhaps simpler versions were more common while elaborate examples remained rare. The archaeological record cannot settle the number. You imagine one final scene in Syracuse. A scholar watches a bronze sphere turn beneath lamplight. Outside, the actual stars appear above the harbour. Inside, a crafted model moves according to human calculation. The two skies are not identical. One is vast and unreachable, the other fits within a room. Yet the smaller one reveals something important about the people who built it. They believed the heavens could be understood well enough to imitate. And that belief may have been the beginning of an entire mechanical tradition now almost completely gone. You face one of the strangest facts surrounding the mechanism. Nothing equally complex survives from the ancient Mediterranean for many centuries. Historians know that gears existed, that astronomical models were described, and that engineers built sophisticated devices. Yet the archaeological record presents no neat chain leading from this machine toward later clockwork. The silence between those surviving technologies is not proof that knowledge vanished instantly. It is evidence that preservation, transmission, and historical visibility can fail in ways that make technological history look far simpler than it really was. Bronze is a poor material for leaving descendants. It is durable when buried under favourable conditions, but it is also valuable, recyclable, and easy to reuse. A damaged scientific instrument could become raw material for a vessel, fitting, weapon, statue repair, or coin. Wooden components rot, leather straps disappear, wax tablets deform, papyrus burns or decays. Even if a workshop produced many intricate machines, the odds of one surviving intact across 2,000 years would remain extraordinarily small. This creates a dangerous illusion. You walk through a museum and see rows of stone sculptures, ceramic jars, coins, and inscriptions, because these objects survive in large numbers. They begin to define your mental picture of the ancient world: fragile machines, wooden measuring devices, textile tools, and specialized workshop instruments vanish from that picture simply because their materials were less fortunate. Archaeology records durability more faithfully than importance. Researchers at major universities have repeatedly emphasized this problem when studying ancient technology. Material survival is uneven, and the absence of an object cannot automatically prove the absence of a tradition. Historians therefore combine archaeology with literary evidence, inscriptions, experimental reconstruction, and comparisons with later mechanical practices. The Antikythera Mechanism forces that caution upon you. Its complexity seems too developed to emerge without predecessors. A maker does not usually begin by producing a compact machine with many interacting parts and several astronomical functions. Such work suggests earlier experimentation, simpler models, failed attempts of specializers tools, and inherited techniques, yet almost all of that developmental history is missing. You can imagine generations of objects that leave no trace. A teaching model made mostly from wood may survive only a few decades. A bronze demonstration device might be dismantled after breaking. A workshop prototype could be melted immediately because its material remains useful. An instrument owned by a wealthy family might disappear during a political turmoil, fire, looting, or inheritance disputes. Nothing mysterious is required. Ordinary life destroys technology very efficiently. The comparison with later mechanical clocks is tempting because medieval European clockmakers eventually built elaborate gear systems to measure time. Yet direct continuity from Hellenistic astronomical mechanisms to medieval clockwork has not been securely demonstrated. The gap in surviving evidence is too large, and mechanical traditions develop differently across regions. Scholars continue to debate whether some knowledge passed indirectly through Byzantine, Islamic, or other technical traditions, mechanical texts, astronomical instruments, and geared devices certainly continued to exist in various forms across late antiquity and the medieval world. However, tracing one continuous lineage from the Antikythera mechanism to later clocks remains difficult. That uncertainty is more interesting than a simple story of disappearance. Knowledge rarely vanishes everywhere at once, it fragments. One workshop may preserve gear cutting while losing advanced astronomical modelling. Another region may retain mathematical astronomy but express it through tables rather than machines. Elsewhere, automata survive as courtly entertainment while precision gearing develops for different purposes. Technology can break apart into separate traditions. You picture a complex tree losing branches. Some grow elsewhere, some wither. Some survive only as descriptions copied by scribes who have never seen the original devices. Centuries later, another craft tradition may rediscover a similar principle through entirely independent experimentation. The result looks like interruption. The reality may be more tangled. A quirky thought experiment helps. Imagine that almost every modern electronic device disappeared, leaving only one damaged scientific calculator buried in unusual conditions. Future archaeologists might discover buttons, circuitry, and a display, then struggle to decide whether it represented a common technology or a unique masterpiece. Without factories, manuals, chargers, household examples, or manufacturing records, the object would appear almost impossibly advanced relative to other surviving artifacts. The comparison is imperfect but revealing. The Antikythera mechanism may be suffering from the same archaeological loneliness. Its isolation does not mean it was common, it also does not mean it was unique. Both possibilities remain open, which is why the machine continues to provoke debate. Some scholars favour the idea of a highly specialised but broader tradition. Others prefer greater caution, noting that extraordinary objects can emerge from exceptional workshops without implying widespread production. You listen to the quiet between those positions. The machine itself cannot tell you how many siblings it once had. No warehouse list survives. No ancient catalogue describes a standard model. No workshop account records annual production. Literary references to celestial machines are suggestive but sparse. The physical record therefore leaves you with probabilities rather than certainty. That is where historical imagination must remain disciplined. It is easy to turn absence into fantasy, to invent forgotten industries or secret civilizations unsupported by evidence. The stronger interpretation is more restrained. Ancient technological capability was broader than surviving objects alone once suggested, but its exact scale remains unknown. This restraint does not diminish the mystery. It deepens it. A sophisticated tradition does not need thousands of machines to matter. Even a handful would reveal that ancient craftsmen could solve problems previously thought beyond their mechanical reach. A small workshop network can carry advanced knowledge for several generations, then disappear without leaving a large archaeological footprint. You picture one of the final makers in such a tradition. He opens a chest containing old templates, worn tools, and partially completed gears. Perhaps he learned from a teacher who learned from another master decades earlier. The workshop receives fewer commissions now. Patrons prefer different luxuries. Political priorities have shifted. Skilled apprentices choose occupations with steadier income. One tradition begins to thin. The knowledge is still real, but fewer people carry it. Eventually, a difficult repair is no longer attempted. An old instrument breaks and is discarded. A box of templates burns in a household fire. A craftsman dies without training a successor. No historian is present to mark the moment. There is no ceremony for lost technique. That may be why technological disappearance feels so unsettling. Civilizations usually notice the collapse of armies, dynasties, and cities. They do not always notice the death of a specialized craft. The loss happens quietly, sometimes within one room. The mechanism therefore challenges a comforting assumption about progress. You may imagine human technology as a staircase, each generation climbing higher than the last. Archaeology suggests something more fragile. Skills can advance, plateau, disperse, and disappear. Complex knowledge can become simple memory. A machine can outlive the tradition that made it. Researchers studying ancient engineering increasingly treat technological history as a landscape of uneven development rather than a straight ascent. Some regions become highly sophisticated in one field while remaining ordinary in another. Some inventions appear early, then find little practical demand. Others flourish only when political and economic conditions support them. The mechanism fits this pattern perfectly. Its existence proves capability. Its rarity proves almost nothing about its scale. That distinction is essential. You can feel how easily the past becomes distorted when only durable materials survive. Stone temples appear timeless because they remain visible. Fragile scientific instruments become invisible because they do not. The surviving world is therefore heavier, harder, and simpler than the living world once was. The lost world may have contained more movement, more wood turning on wooden axles, more bronze pointers crossing painted scales, more workshop prototypes that were never meant to last, more technical conversations that disappeared with the people who understood them. You imagine opening a storeroom in an ancient scientific workshop. Shelves hold unfinished instruments, templates hang from pegs, a damaged gear waits for repair, a wooden model demonstrates a celestial cycle, notes sit beside tools covered with calculations. Then the room fades. The wood rots first, paper and wax disappear, bronze leaves through recycling, the building collapses, centuries pass. What remains is almost nothing. And from that almost nothing, one corroded mechanism survives to suggest that the missing tradition may have been far richer than the silence around it allows you to see. You enter a Mediterranean world being drawn steadily into Roman power, where Greek cities, workshops, libraries, and educated households now exist beneath a political order centered farther west. Conquest does not erase Greek knowledge. In many cases, it increases Roman appetite for it. Wealthy families collect Greek sculpture, employ Greek tutors, read Greek philosophy, and commission objects associated with learning. Scientific instruments can therefore travel alongside art, books, and luxury goods carried into a society eager to possess the prestige of Greek culture. This movement of knowledge is complicated. Rome conquers Greek territories militarily, yet Roman elites often admire the intellectual traditions of the people they defeat. Greek physicians work in Roman households, Greek teachers educate aristocratic children, philosophical schools attract Roman students, astronomical ideas enter Latin literature, while Greek technical knowledge continues circulating through educated networks. The relationship is never simply one of replacement. It is a long process of adoption, adaptation, admiration, and selective neglect. You can picture a Roman villa overlooking the sea. Marble stools line a garden, painted walls imitate architectural spaces, shelves hold scrolls copied from Greek authors. Somewhere in a private room, a complex astronomical instrument could easily belong among these displays of cultivated taste. Its owner might value it because it demonstrates learning, because it entertains guests, or because its moving pointers make difficult celestial ideas easier to grasp. Records confirm that Roman writers knew of mechanical models associated with Greek science. Cicero, writing in the 1st century before the Common Era, described devices said to reproduce celestial motions. He refers to mechanical spheres connected with respected Greek thinkers, including Archimedes. Such passages do not describe the Antikythera mechanism directly, but they show that Roman intellectual circles were familiar with the concept of machines representing the heavens. That detail is important. The mechanism would not necessarily have seemed impossible to an educated Roman observer. It might have seemed rare, expensive, ingenious, and worthy of conversation, but not beyond the imagination of the age. A Roman collector familiar with Greek science could understand such an object as part of a prestigious intellectual tradition. Prestige, however, can be dangerous for technology. An instrument valued mainly as a curiosity may survive only while someone cares about its function. If an owner dies, heirs may not understand it. If a gear breaks, the household may lack a specialist capable of repair. If fashions change, an object once admired can become clutter. Bronze then regains its value as metal rather than machinery. The transformation is painfully simple. A broken scientific device may cease being science the moment nobody remembers how to use it. You imagine a servant opening a storage chest decades later. Inside rests a complicated object with stiff pointers and damaged plates. The inscriptions are difficult. No knowledgeable teacher remains nearby. To the servant, it may be no more meaningful than an old instrument belonging to a dead master. Knowledge depends on recognition. Roman society inherited enormous amounts of Greek intellectual material, but inheritance never guarantees equal preservation. Some texts were copied repeatedly because schools considered them essential. Others faded because readers lost interest. Some crafts flourished under Roman patronage. Others may have narrowed as economic demand shifted. Major university scholarship on the Roman adoption of Greek science emphasizes this uneven process. Roman authors admired Greek mathematics and natural philosophy, yet Roman technical culture often favored applications tied to architecture, surveying, military engineering, hydraulics, agriculture, and public works. This does not mean Romans lacked theoretical interests. It means different kinds of knowledge enjoy different levels of support. A compact astronomical machine occupies an uncertain place within those priorities. It is intellectually impressive, but it does not build roads. It does not move water into cities. It does not measure farmland for taxation. It does not raise siege engines or improve harbour construction. its value is subtler, residing in education, prediction, display, and understanding. Such technologies are often more vulnerable than practical infrastructure. An aqueduct receives repairs because thousands of people need water. A specialized astronomical instrument may receive repairs only if one patron cares enough to pay for them. That difference can determine survival. You hear sandals crossing a tiled floor. An educated Roman guest enters a study where a Greek teacher demonstrates a celestial model. The teacher turns a control while explaining how the moon moves through a cycle. The guest watches closely, fascinated by the tiny mechanical order. The machine becomes a bridge between cultures. Its bronze may have been worked in a Greek workshop. Its astronomical principles may reflect traditions reaching even farther east. Its customer may be Roman. Its explanation may be delivered in Greek to someone whose political power comes from Rome. Technology travels because people travel. There is a quirky possibility that some instruments were transported as war booty. Roman generals famously carried Greek art, manuscripts, and luxury objects westward after military victories. A complex scientific machine could theoretically have entered Roman possession through similar channels, although no surviving evidence proves that this happened with the Antikythera Mechanism. The idea remains plausible only in a broad cultural sense. Conquest moves objects without preserving their original context. A machine taken from a scholarly setting and placed in an aristocratic collection may keep its beauty while losing part of its intellectual environment. The object survives physically, but the network of teachers, craftsmen, and tradition surrounding it becomes thin. That kind of survival can become a form of loss. Scholars continue debating how much Hellenistic scientific practice remained active under Roman rule and how much change as institutions, patronage, and cultural priorities shifted. Some emphasize continuity, pointing to ongoing astronomical study, engineering, and mathematical writing. Others note that certain highly specialized traditions become harder to trace in surviving evidence. The disagreement reflects a larger problem. Political continuity and technical continuity are not the same thing. An empire can remain powerful while a small craft disappears. A city can grow richer while a specialized workshop closes. A library can preserve theoretical texts while practical manufacturing knowledge fades outside its walls. The mechanism belongs precisely to this fragile zone. You imagine a Roman collector purchasing an astronomical device because it demonstrates sophistication. Guests gather around it during an evening meal. Someone asks whether the machine can predict an eclipse. Another admires the engraving. A third simply enjoys the novelty. Years pass. The collector dies. Perhaps his son prefers racing horses. Perhaps his daughter values the library but not the mechanical devices. Perhaps the household retains the machine but uses it rarely. Its meaning begins to thin. The object still exists, yet active knowledge surrounding it becomes weaker. A later owner may display it without understanding every dial. Another generation may store it. Eventually, a craftsman is asked whether the bronze can be reused. This imagined sequence cannot be proven, but it demonstrates how easily complex technology can disappear without civilization itself collapsing. That point matters greatly. Lost technology is often described as though a dramatic catastrophe must erase it. In reality, neglect can be more effective. A technique dies when too few people practice it. A device becomes obsolete when nobody commissions replacements. A complex tradition can shrink quietly inside a prosperous society. Romanticism power therefore creates both opportunity and danger for Greek scientific instruments. The empire connects distant regions through trade, roads, ports, and elite networks. Objects can travel farther than ever. Wealthy patrons can fund expensive craftsmanship. Greek intellectual traditions find eager Roman audiences. Yet circulation can separate objects from the communities that created them. A machine becomes collectible. A scientific instrument becomes decoration. A working model becomes an heirloom. That transformation is subtle enough to escape historical notice. You picture bronze catching lamplight in an elegant Roman interior. The gears still move, the pointer still follows its scale, the mathematics remains perfectly embedded inside the metal. But knowledge is more than mathematics. Someone must know why the machine moves, someone must understand how to repair it. Someone must care enough to teach the next person. Without those people, even the finest mechanism becomes silent. You stand for a moment in that imagined room while distant conversation fades. The instrument rests on a table between two worlds, Greek in intellectual ancestry and Roman in possession. It has crossed political boundaries more easily than its technical tradition can. Empires inherit objects quickly. They inherit understanding more slowly. And sometimes what appears to be preservation is only the beginning of forgetting. A new kind of archaeology begins when light is no longer enough. The mechanism's most important parts are buried beneath corrosion, pressed together in fragile layers that cannot simply be pulled apart without risking permanent damage. So researchers turn to methods that allow them to see through the bronze. You imagine the object resting inside a laboratory, surrounded not by chisels or brushes, but by carefully controlled machines capable of revealing structures hidden inside metal. The goal is simple in principle. Researchers want to know what survives beneath the visible surface. In practice, and the problem is difficult, corrosion has changed the density of the material. Broken pieces overlap, cracks distort shapes, mineral growth fills spaces that once stood empty. A gear hidden inside a fragment may be partly crushed, partly missing, and partly obscured by another component. Radiographic imaging changes the investigation. Instead of relying only on exposed surfaces, researchers begin studying internal layers. Dense areas block radiation differently from thinner areas, producing images that reveal buried forms. A wheel that has not been visible for centuries appears as a faint circle. Tooth patterns emerge, axle positions become clearer. Researchers can compare the geometry of these hidden structures with visible gears and begin rebuilding the machine virtually. This is archaeology without owning the object. The technique becomes especially powerful when images are taken from many angles. Computer processing can combine those views into three-dimensional representations of the fragments. Researchers then examine virtual slices through the corroded mass, moving layer by layer through material that remains physically untouched. The experience must feel almost impossible. You imagine looking at a screen and watching bronze become transparent. A hidden plate appears beneath another. A gear tooth emerges from darkness. A line of lettering becomes visible where no ordinary camera could reach. The object is still broken, but the breakage is no longer completely opaque. Research teams connected with major British universities and scientific institutions used advanced imaging to transform modern understanding of the mechanism. Their work revealed previously unreadable inscriptions and helped establish the arrangement of the internal gear systems with far greater confidence. The machine began to yield information that earlier generations could not access simply because the necessary technology did not yet exist. There is an elegant irony here. A device built with ancient metalworking becomes understandable only through modern imaging. Yet the modern technology does not replace historical reasoning. A scan reveals shapes, not explanations. Researchers still have to decide which gear belongs where, what a damaged tooth count probably was, and how a particular inscription relates to a dial or astronomical cycles. The image provides evidence. Interpretation builds the machine. One hidden gear may appear incomplete, with several teeth missing from corrosion. Researchers estimate the original count by measuring the surviving arc and spacing. Another fragment may preserve only part of a circular inscription. Specialists compare letter forms and spacing to reconstruct missing words. Every reconstruction carries degrees of certainty. Some elements are firmly supported because the physical evidence is clear. Others remain plausible rather than proven. Researchers must constantly separate what the fragments demonstrate from what a complete astronomical model would ideally require. That discipline is essential. A beautiful reconstruction can still be wrong. You can imagine the temptation to fill every missing space. The surviving machine suggests such extraordinary sophistication that the mind naturally wants completeness. Yet archaeology rewards patience more than elegance. A missing component must not be invented simply because it would make the system more satisfying. This tension has produced ongoing scholarly debate. Some reconstructions propose a more elaborate front display containing indicators for the known planets. Others adopt a more conservative approach, emphasizing only the parts for which surviving evidence is stronger. Researchers compare inscriptions, gear locations, ancient astronomical theories, and available physical space inside the case. The disagreement is productive rather than embarrassing. It reveals how science works when evidence is incomplete. One quirky detail is that modern researchers sometimes create physical replicas or computer models to test whether proposed gear arrangements actually work. A reconstruction may look convincing on paper but fail when the gears are assembled. Components collide. Axles overlap. Ratios do not behave as expected. Mechanical reality becomes a referee. That is fitting for this particular artifact. The original maker faced the same problem. A theory only mattered if the bronze turned properly. Modern scholars encounter the machine through the same practical constraint. Their models must move. You hear a quiet click in your imagination. A reconstructed gear train rotates on a laboratory bench. One pointer advances, another turns more slowly. A proposed arrangement either behaves as predicted or exposes an error. The ancient mechanism tests modern understanding. Researchers have also used specialized surface imaging to recover inscriptions too faint for ordinary photography. Different lighting angles reveal microscopic changes in depth. Letters almost erased by corrosion become legible because shadow exaggerates their remaining grooves. The words return slowly. A name emerges. A number appears. A fragment of an astronomical instruction becomes readable. These discoveries are often small, but their implications can be large. A few letters may identify a celestial body, a number may support a particular cycle. A technical phrase can reveal how the user interpreted a display. The machine contains its own commentary. This is what makes the inscriptions especially valuable. Gears show what the mechanism did. Text can sometimes explain what the user was expected to understand. Researchers at institutions such as University College London have used combinations of imaging, epigraphic analysis, and mathematical reconstruction to propose increasingly detailed models of the mechanism's front display. Their work has attracted considerable attention because it suggests that the device may have represented more of the ancient cosmos than once thought. Yet important uncertainties remain. The front portion is badly incomplete. Large structural elements have vanished. Several proposed gears are inferred from inscriptions and astronomical requirements rather than directly preserved. Scholars therefore continue discussing how much confidence should be placed in complete reconstructions. That open debate is healthy. You are not watching a mystery being solved once and for all. You are watching a mystery become better defined. The distinction matters. Every technological advance in imaging reduces some uncertainty while revealing new questions. A previously invisible gear appears, but then its function must be explained. A hidden inscription becomes readable, but its wording introduces another astronomical problem. Knowledge expands by producing sharper puzzles. There is something soothing about that process. The artifact does not surrender everything at once. It rewards repeated attention. New instruments allow researchers to return to the same fragment decades later and ask different questions. The bronze has not changed much, but the ability to see it has. This creates a strange relationship between ancient and modern technology. The mechanism represents one lost technological tradition. The scanning machines represent another civilization's attempt to recover it. One culture encoded astronomy in gears. Another decodes those gears through radiation and computation. Neither process is simple. You imagine the fragment placed carefully inside a scanner. The room is quiet. Researchers step away while the machine begins its work. Invisible energy passes through bronze, corroded by 2,000 years of salt water. Data accumulates. Later, specialists gather around a screen. A structure appears. Perhaps it is a wheel. Perhaps an inscription. Perhaps the faint outline of something no one expected. That moment is not dramatic in the theatrical sense. There is no thunder, no sudden revelation of a complete machine. There is only a small increase in clarity. But history often returns in exactly that way. A few more teeth become visible. A few more letters are read. A few more relationships become possible. And slowly, the ancient machine begins to exist again, not as a restored object, but as a structure reconstructed inside the minds of people who can finally see beneath its surface. The surviving fragments offer only part of the original machine, and this incompleteness forces modern researchers into a delicate kind of reconstruction. You're no longer simply asking what a visible gear does, you're asking what missing gears must once have existed for the entire astronomical system to make sense. The task resembles rebuilding a shattered clock when several wheels, plates, pointers, and sections of the case have vanished completely. Every proposal must satisfy the surviving metal, the inscriptions, the available space, and the astronomical relationships the machine appears designed to represent. This is where reconstruction becomes both science and restraint. A proposed model cannot merely look convincing. The gears must fit inside the dimensions suggested by the fragments. Axles cannot pass through solid plates without evidence. Tooth counts must produce appropriate ratios. Pointers must align with the scales. The arrangement must also remain mechanically plausible when the system turns. A solution that satisfies astronomy but causes gears to collide is not a solution at all. You imagine researchers working with drawings spread across a table. One sketch shows a possible arrangement of planetary indicators, another calculates how many teeth a missing wheel might require, a third maps the positions of surviving holes and bearings. Each page contains possibilities, but only a few combinations can survive every constraint at once. The front display presents the greatest challenge. Large portions are missing, yet surviving inscriptions strongly suggest that it once represented more than the sun and moon alone. References to planetary behavior have encouraged scholars to investigate whether the known planets visible to the naked eye were represented by separate indicators. Such a system would dramatically increase the mechanical complexity of the front assembly. Ancient observers recognized Mercury, Venus, Mars, Jupiter, and Saturn as wandering lights against the background stars. Their apparent motions could be complicated. A planet might slow, stop, and seem to reverse direction before continuing forward again. Any machine attempting to represent those patterns mechanically would need carefully designed combinations of circular motion. You can sense the difficulty immediately. A simple pointer can rotate steadily around a dial. A planetary indicator requires something more subtle if it is meant to imitate irregular apparent motion. Researchers therefore compare surviving evidence with ancient Greek astronomical models based on combinations of circular paths. This comparison does not guarantee the original design. It establishes what may have been possible. Teams associated with major research universities have proposed detailed reconstructions in which nested gear systems create planetary motions across the front display. These models draw upon surviving inscriptions, known ancient astronomical theory, and the physical geometry of the mechanism. Their work demonstrates that a complete mechanical cosmos can be designed within the approximate space available. That achievement is impressive even when some parts remain hypothetical. You picture a reconstructed front face filled with concentric circles and small pointers. The sun advances steadily. The moon shifts according to its own cycle. Planetary indicators move with varying speeds, sometimes appearing to reverse relative to the surrounding scale. The whole display resembles a miniature sky translated into geometry. Yet not every scholar accepts every detail. Some researchers argue that the missing evidence leaves too much room for alternative arrangements. Others consider the inscription strong enough to support a more ambitious reconstruction. The debate concerns not whether ancient astronomers understood planetary cycles, but exactly how those ideas were embodied in this particular machine, as that distinction keeps speculation disciplined. One curious feature of the reconstruction process is that missing parts can sometimes be constrained by empty space. If a gear must connect two surviving components, researchers can estimate how large it could have been before striking another wheel. The absence of material becomes a measurable boundary. Even emptiness contains information. You imagine a circular gap inside the case, so nothing survives there now. Yet neighbouring axles and plates define a narrow region where some component almost certainly turned. Researchers calculate possible diameters, gear counts, and positions until a workable solution emerges. This is mechanical archaeology at its most abstract. The machine is rebuilt partly from objects and partly from relationships. A surviving tooth count may imply another wheel of a certain size. A dial inscription may require a pointer with a particular behaviour. A mathematical cycle may demand a ratio that only certain gear combinations can produce. The reconstruction becomes a web of constraints. Researchers often test their ideas through physical replicas. Metal, wood, or plastic, or other modern materials can reproduce the proposed geometry without pretending to recreate ancient workmanship exactly. When a model turns smoothly, it demonstrates mechanical feasibility. When it jams, the reconstruction must be reconsidered. This process has an almost playful quality. You turn a replica slowly and watch a pointer advance. The movement either matches the intended cycle or drifts away from it. A few degrees of error may reveal a mistaken assumption made many steps earlier. The machine does not tolerate wishful thinking. One fringe interpretation imagines that the original front display may have been even more elaborate than any modern reconstruction, possibly including decorative celestial imagery or additional indicators now completely lost. Such ideas remain possible in a general sense because large portions are missing, but they cannot be established without physical or inscriptional support. The safer conclusion is already remarkable. The surviving evidence strongly suggests that the mechanism was designed as a coordinated model of celestial motion rather than a collection of unrelated dials. Its parts belong to a unified concept of the cosmos. That unity matters. A calendar instrument can be built one dial at a time. A celestial model requires integration. The motion of one pointer must relate coherently to others. The user should be able to set a date and see several astronomical relationships update together. You place your fingers on the imagined control. One motion enters the machine. Inside, the movement divides. One gear rotates rapidly, another turns slowly. A pin moves through a slot. A pointer advances across one scale while a different indicator moves elsewhere. The machine behaves like a small mechanical argument. It says that many celestial phenomena can be understood as parts of one ordered system. That idea has deep roots in ancient philosophy, but here it becomes physical. The cosmos is not merely described as harmonious. It is built as harmony. Researchers working on complete reconstructions face another practical question. How did the original user read the display without becoming confused? Too many pointers and one face could be difficult to distinguish. Some proposed models therefore consider colour, labels, small markers, or decorative forms that may have helped separate celestial bodies visually. Most of those surface details are lost. Yet the inscriptions suggest careful attention to explanation. This strengthens the possibility that the completed machine was visually organised rather than mechanically chaotic. Its maker understood that complex information must remain readable. You imagine the finished device fresh from the workshop. The bronze is polished rather than corroded, lettering is crisp, pointers are thin and distinct, the wooden case has clean edges. Perhaps coloured details separate one celestial indicator from another. The object does not look ancient to its owner. It looks new. That simple thought changes the reconstruction completely. Modern eyes encounter fragments. Ancient eyes encountered design. They saw proportion, surfaces, colours, labels, and movement arranged exceptionally. They did not need to imagine the missing pieces because nothing was missing. The machine's original completeness may therefore have been its most persuasive features. A user turns one control and watches a coherent cosmos respond. Every motion confirms another. The experience would make astronomical the theory almost inevitable. Yet the modern reconstruction remains provisional. Scholars can build increasingly convincing models, but the missing bronze prevents absolute certainty. New readings of inscriptions may shift an interpretation. A previously unnoticed feature may force another redesign. Competing models may remain plausible for years. This openness is not failure. It is fidelity to the evidence. You can feel how tempting a final answer would be. A perfect reconstruction would close the case. But history rarely offers such comfort. The most careful researchers live with several levels of certainty at once. Some functions are secure, others are strongly supported, others remain possible. The mechanism teaches patience because it cannot be restored by confidence alone. You stand before a modern reconstruction and watch its pointers move. The machine seems whole. For a moment, the missing ancient parts feel almost present. Then you remember that the model is an argument built from fragments. Its elegance reflects both ancient ingenuity and modern reasoning. And perhaps that is the most fitting way to encounter a lost technology. Not as something fully recovered, but as a structure slowly returning through evidence, mathematics, and imagination. The question of uniqueness settles over the mechanism like a quiet shadow. You can see why it is tempting to imagine a solitary genius creating one extraordinary machine that had no true relatives. History loves singular objects because they seem easier to understand. One masterpiece, one inventor, one moment of brilliance. Yet technology rarely develops so neatly. And the mechanism itself contains too many signs of mature practice to make complete isolation feel entirely comfortable. A complex geared instrument requires more than inspiration. It requires established methods for dividing circles, cutting teeth, fitting axles, laying out plates, and translating astronomical ratios into motion. Those procedures could, in theory, be invented by one exceptional workshop, but repeated success becomes more likely when skills already exist. The machine looks less like a crude experiment and more like the product of a tradition confident enough to compress many functions into a compact case. You imagine several workshops spread across the Eastern Mediterranean. One produces simpler calendar devices, another specializes in mechanical demonstrations, a third serves wealthy patrons interested in astronomy. Not every instrument needs to match the Antikythera mechanism. Some may contain only a few gears. Others may use wood for components that would never survive archaeologically. A handful may reach similar complexity, but disappear through recycling or decay. This possibility remains plausible precisely because preservation is selective. Bronze was valuable. Wood was vulnerable. Scientific instruments were portable. None of these traits favours survival. A monumental stone structure can remain visible for thousands of years because nobody can casually carry it away. A small machine can vanish during a single household clearance. That simple contrast matters. Researchers at major universities and archaeological institutions often caution against treating the surviving record as a complete inventory of ancient capability. The lack of comparable machines does not prove there were none. At the same time, responsible scholarship cannot assume a large hidden industry without evidence. The safest conclusion rests between those extremes. The mechanism may be unique in survival, without being unique in existence. That distinction opens several possibilities. Perhaps a small number of elite instruments circulated among scholarly and wealthy circles. Perhaps workshops built customized machines rather than standardized models. One patron might request astronomical displays, another calendrical functions, and another a moving demonstration of celestial theory. Such production would leave little repetition. You would not expect identical copies. You would expect families of related techniques. Literary evidence strengthens this possibility. Ancient authors refer to mechanical celestial models and sophisticated demonstrations, suggesting that the concept itself was not unknown. Those texts do not give you surviving gear counts or workshop inventories, but they indicate that machines imitating heavenly motion belonged within the intellectual imagination of the period. That matters because inventions need audiences. A craftsman will not spend months building a complicated astronomical device if nobody understands why it is valuable. The existence of patrons, teachers, and scholars interested in such objects makes repeated production more plausible. You can imagine a network rather than a factory. A mathematician hears of a mechanism built on roads. A wealthy visitor sees it demonstrated and commissions another version. A craftsman copies part of the design but changes the scale. An apprentice learns the gear-cutting methods and later works elsewhere. Knowledge moves through people. Objects follow. The resulting tradition could spread without ever becoming common. This is how many specialized technologies survive before industrial production. A handful of expert makers serve narrow markets. Their products differ from one another. Skills are transmitted through apprenticeship rather than manuals. If the chain breaks, the tradition can disappear quickly. One curious analogy comes from ancient musical instruments. Archaeologists rarely find complete wooden instruments because the material decays. Yet texts, images, and scattered fittings reveal that musical craftsmanship was highly developed. The absence of surviving instruments does not imply ancient people lacked them. The same logic may apply to machinery. A geared device made partly of wood might leave almost nothing recognizable. Bronze pins or fittings could survive separately without revealing the form of the original machine. Archaeologists might catalogue them as ordinary hardware. Lost context can make advanced technology look mundane. You picture a single corroded gear excavated from an ancient building. Without neighbouring components, it might seem like part of a simple device. Add 10 more gears and an astronomical inscription, and the interpretation changes completely. The Antikythera Mechanism benefits from surviving as a cluster. Its fragments confirm one another. Most hypothetical relative may not have been so fortunate. Scholars continue debating whether the object represents the high point of a mature tradition or an exceptional synthesis created by an unusually gifted team. Both interpretations remain possible because neither can be proven from one surviving example. The debate it both reveals thing important. Uniqueness is difficult to measure when evidence is sparse. You can know that an object is rare in museums. You cannot easily know whether it was rare in life. That gap encourages speculation, so caution becomes essential. A fringe claim sometimes suggests that the mechanism proves the existence of an entire lost technological civilization comparable to much later industrial societies. The evidence does not support that. There are no ancient factories filled with standardized precision machinery, no widespread infrastructure dependent on geared computation, and no archaeological signs of mass mechanical production. The real story is subtler. A society does not need industrialization to produce highly sophisticated specialist objects. Skilled workshops can create remarkable machines while most daily technology remains comparatively simple. This unevenness is common throughout history. A culture may build extraordinary astronomical instruments while ordinary farmers continue using traditional tools. A court may sponsor elaborate automata while nearby villages change very slowly. Advanced knowledge can exist in narrow social pockets. The mechanism fits that pattern comfortably. Its sophistication does not require an entire population to understand gear ratios. Only a small group needs the necessary expertise. That group may include astronomers, mathematicians, metalworkers, engravers, and wealthy patrons. You imagine the social distance between them and an ordinary labourer. A dock worker might handle the crate without knowing what it contains. A farmer may never see such a device. A merchant may understand only that it is expensive. A scholar sees a model of the cosmos. All live within the same civilization. Technology is distributed unevenly. This helps explain why disappearance can be so complete. When knowledge is concentrated among a few specialists, loss becomes easier. A war does not need to destroy an entire society. A shift in patronage does not need to impoverish everyone. A few workshops closing may be enough. Specialized traditions are fragile because they are narrow. You can hear the quiet of an abandoned workspace. Tools remain on hooks. Half-finished plates collect dust. The master has died. The apprentice has moved into another trade. No customer arrives asking for a celestial machine. The knowledge still exists in fragments, but not in one living person. That is how uniqueness may be created retroactively. Not because only one machine was ever made, but because only one survives clearly enough to reveal the tradition. Modern archaeology often encounters this problem. A rare object suddenly appears and forces historians to ask whether it is an anomaly or a survivor from a missing category. Sometimes later discoveries answer the question, sometimes they do not. The mechanism remains suspended between those possibilities. You can imagine future excavations finding another geared fragment in a completely different context. Perhaps it carries an inscription. Perhaps its tooth spacing resembles known ancient workmanship. One discovery could dramatically change the debate. But no such confirmation is needed to understand the larger lesson. The past contains missing categories. You cannot assume that what survives represents everything people once made. The mechanism proves that at least one ancient workshop reached an extraordinary level of mechanical astronomy. It does not reveal how many others did. Perhaps the number was 5. Perhaps 50? Perhaps 1? The evidence remains quiet. That uncertainty is not frustrating if you allow it to remain open. It gives the object its most haunting quality. You're looking at something that might be a masterpiece without peers, or the lone survivor of a family whose other members have completely vanished. Both possibilities are extraordinary, and somewhere between them lies a technological world you can only partially recover. You move away from the surviving mechanism and into the quieter question of disappearance. Technology is often imagined as something that advances whenever intelligent people discover better methods. Yet complex knowledge depends on far more than intelligence. It needs institutions, materials, teachers, apprentices, customers, trade routes, political stability. and enough wealth to support people who spend time making difficult things. When several of those supports weaken together, a sophisticated crop can fade without any single dramatic catastrophe announcing its end. Consider the workshop itself. A precision instrument requires trained labour, and trained labour requires years of instruction. A young apprentice must learn how to prepare bronze, shape plates, mark circles, fit axles, and judge whether parts move correctly. None of this happens quickly. If fewer patrons commission expensive astronomical devices, a master craftsman may decide that training an apprentice is no longer worthwhile. The apprentice, quite sensibly, chooses a trade with steadier demand. The knowledge chain grows thinner. Economic change can be enough to start the process. A wealthy court may support scholars and instrument makers during one generation, then reduce spending during the next. Merchants may stop importing certain materials. Political boundaries may complicate travels. Taxes may rise. Private fortunes may shift towards a land. Architecture, military display, or other forms of prestige. A difficult machine is vulnerable to all of these changes. Major university research into the ancient Mediterranean has shown that scientific activity depended heavily on patronage and institutional stability. Scholars could flourish in cities where rulers, temples, schools, or wealthy families supported intellectual work. When those systems changed, some branches of knowledge remained strong while others weakened. The survival of a theory did not guarantee the survival of a craft. This distinction is easy to miss. A mathematical idea can be copied cheaply compared with a complicated bronze instrument. A text requires writing material, literacy, and someone interested enough to reproduce it. A machine requires all of that knowledge, plus metal, tools, skilled labour, and practical construction methods. Theory can survive while machinery disappears. You can imagine an astronomical manuscript being copied centuries after the workshop capable of building its physical model has vanished. A scholar still understands a celestial cycle. He can calculate it. He can explain it. But he cannot cut the gears. That is how technological fragmentation begins. War can accelerate the process, though not always in the dramatic way popular stories prefer. A city does not need to burn completely. Repeated instability is enough. Workshops close temporarily, and skilled families move elsewhere. Markets become unreliable. Patrons delay expensive commissions. Then temporary disruption becomes permanent. The Hellenistic and Roman Mediterranean experienced frequent political conflict, civil wars, shifting kingdoms, and changing centres of power. Some cities prospered while others declined. Intellectual communities adapted, moved, or disappeared. A specialised workshop dependent on a narrow circle of customers might not survive several generations of uncertainty. You hear shutters closing against a dusty street. Inside, tools are wrapped away. No final ceremony takes place. A craftsman simply receives fewer orders. There is something deeply ordinary about this kind of loss. Technology often vanishes through inconvenience. A complicated object becomes too expensive to maintain. A simpler alternative meets most practical needs. A customer sees no reason to pay for precision when a written table provides enough information. Efficiency can destroy sophistication. This sounds paradoxical, but history offers many examples of useful techniques disappearing when social conditions change. A technology may be technically impressive while remaining economically unnecessary. If it does not save enough labour, earn enough money, support state power or attract sufficient prestige, it may fail to reproduce itself. The Antikythera Mechanism may have lived within exactly this danger zone. It represents extraordinary skill, but its practical necessity is uncertain. Calendars could be maintained without it. Astronomical predictions could be calculated through tables. Teachers could draw diagrams. Wealthy collectors could spend money on sculpture, buildings, or books instead. The machine might therefore be brilliant without being indispensable. That difference matters enormously. An aqueduct receives repairs because thirsty cities depend upon it. A mill continues because it processes grain. A road remains important because armies and trade require movement. A rare astronomical instrument can disappear while ordinary life continues almost unchanged. No civilization wakes up feeling poorer. That may be the most unsettling part. One quirky historical pattern appears repeatedly, and specialized crafts knowledge can survive in language long after its practical meaning has weakened. A later writer may copy a technical term without fully understanding the workshop process behind it. Instructions become abbreviated, demonstrations become stories. Eventually, craftsmanship becomes legend. An ancient reader may encounter descriptions of celestial machines built by celebrated thinkers and admire them as marvels from a more ingenious age. The reader does not necessarily know how to reproduce them. The technology becomes memorable precisely because it is becoming rare. Scholars debate how much mechanical knowledge actually disappeared during the transition from the ancient Mediterranean into later periods. Some emphasize decline in particular traditions. Others point to continuity in Byzantine and Islamic engineering, where gears, automata, astronomical instruments, and mechanical ideas continue developing in new forms. Both perspectives can be true. Knowledge does not need to vanish completely to become discontinuous. A technique can disappear in one region while surviving in another. A scientific purpose can fade while the same mechanical principle finds a new application elsewhere. Human knowledge behaves more like a branching river than a straight road. You imagine one stream narrowing while another widens. A geared astronomical device disappears from elite Greek workshops. Mechanical ingenuity survives in water clocks, automata, mills, and other systems. Astronomical calculation continues through texts and tables. Later engineers develop new combinations for different needs. The pieces continue. The original synthesis weakens. This is why historians should be cautious with the word lost. Lost does not always mean forgotten by everyone. It can mean separated. The astronomer keeps one part. The metalworker keeps another. The mathematician preserves a third. But nobody combines them into the same machine. That kind of loss is almost visible. It leaves no dramatic ruins. You can picture an old craftsman teaching fewer secrets each year because there is less reason to preserve them. He knows how to correct a gear by eye. He knows which bronze thickness works best. He knows how much looseness an axle can tolerate. His son chooses another profession. A neighbour inherits the tools. Someone melts the unused plates. The techniques disappear without ever being formally declared obsolete. Open scholarly debate remains over how often such silent losses shaped ancient technological history. Some historians argue that workshop knowledge was more resilient than the surviving artifacts suggest. Others emphasize how dependent specialist crafts were on narrow networks of patronage and apprenticeship. The mechanism cannot settle the debate. It can only make the problem impossible to ignore. Its existence demonstrates that advanced mechanical knowledge once converged inside a working object. Its later isolation suggests that convergence did not remain equally visible through time. You feel the rough surface of an imagined workshop table. The room is almost empty now. A few tools remain. Dust settles where gears were once cut. Outside, the city continues living. Markets open. Children grow. Ships arrive. Civilization has not ended. Only one small tradition has. That is how much of human knowledge disappears. Not with fire. Not with the conquest alone. Not with a single collapse. It disappears because fewer people need it, fewer people fund it, fewer people teach it, And finally, remembers how all the pieces fit together. The world continues. And somewhere inside that continuity, a machine becomes impossible to build. You begin to see how misleading the idea of steady progress can be. Modern life encourages the belief that one invention naturally leads to another, each generation standing securely upon everything discovered before. Yet history is filled with interruptions, forgotten methods, abandoned solutions, and skills that vanish because the conditions supporting them no longer exist. The Antikythera Mechanism sits uncomfortably inside this pattern because it appears far more mechanically sophisticated than the objects that survive around it in time. That does not mean technology moved backward everywhere. It means progress was uneven. A society might advance in astronomy while changing little in agriculture. Another might improve construction while losing specialized metalworking traditions. A mathematical technique could become more refined even as a particular instrument disappeared. Knowledge does not rise as one single tide. It moves in separate currents. Researchers at universities such as Stanford University, Yale University, and Oxford University have long emphasized that technological history must be understood through local conditions, institutions, and cultural priorities. There is no universal ladder climbed at the same speed by every society. Some techniques appear early, flourish briefly, then vanish. Others remain simple for centuries because simple methods continue to work. This is important when looking at ancient machines. You may be tempted to ask why the mechanism did not lead directly to mechanical clocks, automated observatories, or industrial machinery. The question assumes that invention naturally produces expansion. In reality, an invention must find demand, resources, and a community capable of maintaining it. Without those supports, brilliance can remain isolated. You imagine a craftsman developing a particularly elegant gear arrangement. The design works beautifully. A few patrons admire it. Yet nobody builds a large industry around it because the instrument solves no urgent economic problem. The knowledge remains impressive. The market remains small. A century later, the technique becomes rare. This pattern appears throughout history. Ancient engineers built elaborate water-driven devices, automatic doors, theatrical machines, and mechanical curiosities. Some were practical, while others demonstrated ingenuity or entertained elite audiences. Their existence proves technical capability, but not necessarily the economic structures needed for widespread adoption. Capability and transformation are different things. That distinction helps explain why sophisticated devices can appear without producing an industrial revolution. A society might know how to make a complex mechanism while lacking cheap materials, abundant energy, standardized production, large consumer markets, or institutions designed to spread the technology. The invention remains contained inside its original setting. You can almost see the boundary. Inside the workshop, knowledge is advanced. Outside, daily life changes but very little. This unevenness is not failure. It is normal historical development. One quirky example comes from ancient steam-related experiments. Hero of Alexandria described devices using heated air and steam to create motion. Popular retellings sometimes imagine these devices as engines waiting to become factories, yet they existed within a completely different economic and technical environment from much later industrial machinery. The principle was known. The system required for transformation was not. The same caution applies to the Antikythera Mechanism. It would be misleading to describe it as a modern computer simply misplaced in antiquity. The device belongs entirely to ancient science, materials, and craftsmanship. Its achievement is impressive precisely because it emerged from that world. not because it's somehow escaped from another age. Language can distort technology. Calling the mechanism advanced is useful only if advanced means sophisticated within its historical context. It should not imply that ancient societies secretly possessed modern industrial capability. The reality is subtler and more interesting. Ancient specialists could achieve remarkable precision without creating mass production. They could understand complex cycles without modern physics. They could build geared modules without developing mechanical clocks on a continental scale. This teaches you something important about innovation. A discovery does not carry its future inside itself. Human choices determine what happens next. A ruler may fund another instrument. A merchant may decide it is too expensive. A scholar may preserve the mathematics. A craftsman may simplify the design. A later generation may abandon the device entirely. Each decision changes the technological path. Scholars continue debating how much ancient technological development was limited by economics, social structure, energy availability and mercies, or cultural preference. Some emphasize labour systems and the lack of incentives for mechanization. Others warn that ancient societies were more inventive and commercially dynamic than older stereotypes suggest. The debate remains open because no single explanation fits every regional technologies. That uncertainty is useful. It prevents simple stories. A society with enslaved labour may still invest in machinery. A wealthy empire may still neglect certain scientific instruments. A technically brilliant culture may choose not to scale an invention. History rarely behaves according to one rule. You imagine several roads extending from the same workshop. One road leads toward more complex astronomical models. Another leads toward the practical gearing. Another ends because patronage disappears. Another survives only inside written descriptions. Most roads remain archaeologically invisible. The surviving mechanism shows only one intersection. This is why linear progress is such a dangerous mental habit. When evidence is missing, later technology can appear to emerge suddenly. Earlier sophistication can seem impossible because no clear chain survives between them. Historians may underestimate entire traditions simply because the middle stages disappeared. The problem resembles listening to a melody with several missing notes. You still hear enough to recognize structure, but the transitions become uncertain. A fringe interpretation sometimes claims that ancient civilizations repeatedly reached near modern technological levels and then collapsed completely. The archaeological record does not support that sweeping claim. What it does support is more restrained and more unsettling. Highly sophisticated pockets of knowledge could exist and then become invisible. That is enough to challenge comfortable assumptions. You do not need a lost industrial civilization. You need only a small community of experts. Give them mathematics, patient observation, skilled metalworking, and wealthy support. They can create something extraordinary. Remove those conditions. The extraordinary object becomes rare. Remove them for long enough. The object becomes unbelievable. This pattern changes how you look at technological history. Progress becomes less like a staircase and more like a landscape. There are peaks. There are valleys. There are regions where knowledge travels quickly and places where it moves slowly. Some paths connect. Others disappear beneath time. You picture a later craftsman encountering a description of an ancient celestial machine. He understands the words but not the construction. Perhaps he doubts such a device ever worked. That doubt would be reasonable. Without surviving examples to extraordinary claims become stories. This is another way knowledge can disappear. Not by being forgotten completely, but by becoming unbelievable. An ancient author says that a machine reproduced celestial motions. Centuries pass. No one sees such a device. The description begins to sound exaggerated. Then a corroded mechanism emerges from the sea. Suddenly the old claims look different. That transformation is one of archaeology's quiet powers. It does not merely add objects to museums. It changes the range of what historians consider possible. The mechanism tells you that technological history contains surprises because preservation is incomplete. It asks you to hold two ideas at once. Ancient societies were not secretly modern, yet they were sometimes far more technically capable than surviving evidence once suggested. These truths do not conflict. They make history richer. You feel the floor beneath your feet while imagining centuries unfolding around you. Workshops open and close, techniques spread and disappear, empires rise, libraries grow, markets shift. Human knowledge continues moving, but it does not move in one direction. Perhaps that is the deeper lesson hidden inside the gears. Progress can pause. Progress can fragment. Progress can forget. And sometimes, centuries later, one object returns to remind you that the road was never straight. The mechanism invites a larger question, because one lost machine can never remain only one lost machine in your imagination. You begin to wonder what else disappeared, without leaving enough evidence to be recognized. Ancient workshops produced far more than monuments, statues, and weapons. They also made instruments, measuring devices, tools, models, and practical machines whose materials were often fragile, recyclable, or easily misunderstood once their original context vanished. The surviving archaeological record may therefore preserve only the hardest shell of a much richer technological world. Wood is the first great silence. Ancient craftspeople used wood for almost everything because it was common, workable, and versatile. Frames, handles, wheels, cases, measuring tools, furniture, pulleys, models, templates, and experimental devices could all be made from it. Yet ordinary wood rarely survives across thousands of years unless conditions are unusually dry, wet, frozen, or sealed from decay. A sophisticated wooden mechanism can disappear so completely that even its existence becomes difficult to imagine. You picture a workshop shelf holding several wooden instruments. One is a teaching model with rotating circles. Another is a measuring frame. A third has small pegs, cords, and moving pieces used to demonstrate geometry. None is designed for eternity. The owner expects repair, replacement, and eventual disposal. Archaeology sees almost nothing. Major research institutions studying ancient material culture repeatedly emphasize how strongly preservation shapes historical interpretation. Organic materials vanish at far higher rates than stone, pottery, or metal. This creates a distorted picture in which durable objects appear more culturally important simply because they remain visible. The distortion extends beyond wood. Wax tablets could hold calculations, sketches, and temporary plans. Papyrus could preserve technical manuals, workshop notes, or diagrams. Leather might form belts, straps, flexible joints, or protective cases. Textiles could play roles in machines involving tension, winding, filtration, or measurement. Most of these materials disappear quietly. Their loss matters because technology often depends on combinations of materials. A bronze gear alone may not reveal the machine. A wooden frame alone may look like furniture. A cord may leave no treat. A complete device can therefore dissolve into unrelated fragments. You begin to see how easily a category can vanish. Imagine a wooden astronomical model containing only a few bronze pins and one metal pointer. After 2,000 years, the wood is gone. The bronze pieces are scattered. Archaeologists recover 3 small fittings from different soil layers. Nothing announces that they once belonged to a machine. Context is everything. This problem becomes even greater when materials are recycled. Metalworkers valued bronze, iron, lead, and copper because old objects could become new raw material. A damaged scientific instrument might be dismantled and melted without ceremony. The knowledge embedded in its shape disappears while the metal continues into another life. A gear becomes a bowl. A pointer becomes a hinge. A plate becomes part of a statue. Materials are yes. Technology does not. This is one reason lost machinery can leave fewer traces than ruined architecture. Buildings collapse in place. Small instruments move, break, travel, and transform. You can imagine an ancient storeroom being cleared after its owner dies. A relative recognizes valuable sculpture. Books go to someone educated. Ordinary tools are distributed among workers. A strange mechanical object receives less attention because nobody knows how to use it. The bronze goes to a smith. That simple decision removes an entire machine from history. One quirky possibility is that many unidentified archaeological objects were once parts of devices whose functions remain unknown. Museums contain countless small fittings, hooks, discs, pins, rings, and fragments catalogued carefully but without secure purpose. Most probably belong to ordinary objects. A few may have participated in mechanisms that can no longer be reconstructed. This possibility must be treated cautiously. Mystery invites over-interpretation. A strange metal object is not automatically advanced technology. Yet uncertainty remains genuine when context is poor. Researchers often solve such puzzles through comparison with better preserved finds, ancient images, experimental reconstruction, or traces of wear. A hole polished on one side may suggest repeated movement. A groove may indicate a chord. Uneven abrasion can reveal rotational friction. Small marks become clues. You imagine a conservator holding an obscure bronze disc under magnification. The object seems plain until repeated wear appears around its edge. Perhaps it once turned against something else. Perhaps it formed part of a measuring device. Or perhaps it served a completely different purpose. The silence remains. Ancient technical texts create another missing category. Only a fraction of classical literature survives. Entire works by mathematicians, engineers, diggers, architects, physicians, and astronomers are known only because later writers mention them. Others disappear without even leaving a title. This loss may be larger than any missing collection of machines. A technical manual can preserve methods that no artifact explains. It can describe tools, materials, dimensions, procedures, and mistakes to avoid. Without it, archaeology must work backward from surviving objects. You can sense the frustration of system. A machine survives without its manual. A manual survives without its machine. Sometimes neither survives. Scholars at universities such as Oxford University and Yale University have long studied the transmission of classical texts, showing how copying traditions determined which works reached later centuries. Scribes copied books that readers valued. Expensive, obscure, or highly specialized technical writings could disappear when demand declined. No conspiracy is recorded. Neglect is enough. A manuscript needs repeated rescue. Every copy buys another generation. Stop copying and the work begins to die. This raises an open, scholarly debate about how much ancient technical knowledge disappeared through textual loss rather than practical decline. Some historians argue that missing manuals may conceal more sophisticated workshop traditions than surviving literature suggests. Others caution that lost texts should not become containers for inventions unsupported by archaeology. Both cautions matter. Absence permits possibilities. It does not prove them. Still, the scale of textual destruction is undeniable. Famous works survive partly because generations considered them worth copying. Thousands of less celebrated works vanish because nobody made the next copy. You imagine a technical scroll resting unread on a library shelf. Its diagrams explain a mechanical method. Its author expects future craftsmen to understand it. Years pass, the scroll cracks. A later librarian chooses not to replace it. That is the end. Nothing dramatic happens. No flames are needed. Knowledge can disappear through indifference. The same applies to tools. Specialized tools are often difficult to identify because their purpose depends on the technique they serve. If the technique vanishes, the tool can become mysterious. An unusual divider, template, punch, or measuring device may look simple even if it enabled highly precise work. Technology hides inside procedures. A tool does not explain itself. You begin to imagine entire workshop systems that archaeology cannot fully reconstruct. Templates might standardize repeated forms. Jigs might hold parts in alignment. Measuring rods could preserve ratios. Specialized punches could mark gear divisions. Temporary clay or wax patterns might guide metalworkers. Each object appears modest alone. Together, they create precision. Remove the system, and the surviving fragments seem ordinary. That may be one of the deepest lessons of lost technology. Complexity does not always reside in a spectacular machine. Sometimes it resides in organization. A workshop with simple tools can achieve remarkable results if its procedures are disciplined, its measurements reliable, and its knowledge carefully transmitted. Lose those procedures. The tools remain. The capability disappears. You can almost smell wax smoke and cut wood while imagining a technical room that archaeology never preserves completely. Plans hang near a bench. A craftsman checks a template. Another worker prepares a plate. A small device waits for adjustment. The scene feels ordinary. That ordinariness is exactly why it vanishes. History preserves kings more easily than routines. Stone monuments remain visible. Daily expertise disappears into dust. You begin to wonder how many machines never reached the sea, never entered sealed tombs, and never survived beneath unusual soil conditions. Perhaps the answer is very few. Perhaps it is many. No honest historian can know. The mechanism gives only one secure warning. Survival is not the same as existence. What remains is not a complete inventory. It is a sample chosen partly by accident. And when you look into that accident long enough, the ancient world begins to seem filled with invisible objects, missing manuals, vanished tools, and workshops whose knowledge left no monument behind. The mechanism rests quietly in your imagination, no longer as a puzzle demanding one final answer, but as a small surviving witness to a much larger human story. Its bronze gears once turned beneath a polished case, following numerical relationships that connected calendars, lunar cycles, eclipses, and the wandering lights of the night sky. Today, the surviving fragments are incomplete, corroded, and separated. Yet their existence is enough to change the boundaries of what you can reasonably imagine ancient craftsmen achieving. You picture the original instrument on a wooden table, surrounded by the ordinary sounds of a Mediterranean household. A lamp burns gently nearby. Sandals pass across a stone floor. Someone speaks quietly in another room. Outside, evening settles over the rooftops, and the first stars begin to appear. Inside, a hand turns the mechanism. Bronze wheels engage beneath the cane, and several pointers begin their measured journeys. Nothing moves quickly. That is part of the beauty. The machine does not announce its intelligence, it simply works. A pointer advances. A cycle unfolds. A relationship becomes visible. Records confirm that ancient Greek astronomers possessed sophisticated mathematical traditions for describing celestial cycles, while archaeological research demonstrates that the Antikythera Mechanism physically embodied several of those relationships. The device therefore stands at an unusual meeting point between mathematics, astronomy, craftsmanship, and social time. It is not merely an ancient object, it is a material expression of accumulated knowledge. Yet the machine also reminds you that knowledge is not the same as permanence. A civilization may understand something deeply and still lose the ability to reproduce it. A workshop may disappear. A school may close. A technical vocabulary may become unfamiliar. A machine may break without anyone remaining who knows how to repair it. The disappearance can be quiet. No one needs to declare that a technology has been lost. People simply stop making it. This possibility gives the Antikythera Mechanism its particular sadness. The bronze itself survived, but the complete tradition surrounding it did not. You can recover the gears, you can read portions of the inscriptions, you can reconstruct probable relationships, yet you cannot recover every conversation that produced the machine, every experiment that refined it, or every person who learned its construction from another human being. Those people are gone. Their knowledge has become evidence. You can imagine the final moments of a workshop tradition without pretending to know its exact history. A master dies. An apprentice chooses another trade. A patron no longer commissions expensive instruments. A surviving machine is stored rather than used. Eventually, its purpose becomes obscure. Generations pass. The object becomes an old curiosity. Then it disappears into the ordinary processes of human life. Perhaps it is dismantled. Perhaps it is buried. Perhaps it travels inside a ship whose destination it will never reach. The sea keeps it, and centuries later divers find fragments. That chain of events is enough to make the object feel almost impossibly fortunate. The survival of the mechanism depends on accident layered upon accident. The ship sinks in a location where parts remain accessible. The bronze survives in recognizable forms. Divers discover the wreck. Archaeologists recover the fragments. Conservators preserve them. Modern imaging reveals structures hidden beneath corrosion. At every stage, the story could have ended. It does not. Instead, the fragments reach a modern world capable of asking new questions. Researchers can count gear teeth with extraordinary accuracy. Imaging can reveal hidden structures without dismantling fragile material. Computer models can test proposed reconstructions. Astronomical calculations can compare ancient gear ratios with known celestial cycles. Inscriptions can be studied through advanced photography and digital analysis. Modern technology becomes a lens through which ancient technology becomes visible again. There is something quietly circular about that. A machine built to make celestial patterns visible is now examined through machines built by another technological civilization. One generation uses gears to represent time. Another uses radiation, imaging, and computation to recover those gears. The human desire is remarkably similar. You want to understand patterns. You want to make invisible relationships visible. You want to turn uncertainty into something you can examine with your hands, your eyes, or your instruments. That desire is older than any particular machine. It is part of what makes technology possible. You can imagine an ancient observer looking upward and wondering why the moon changes speed. A modern researcher looks downward and wonders how an ancient craftsman represented that variation mechanically. The questions are separated by centuries, but both begin with the same impulse. Look carefully. Measure! Compare! Try again. Scholars continue debating the precise extent of the technological tradition represented by the mechanism. Some regard it as evidence of a broader Hellenistic culture of mechanical astronomy whose surviving examples are exceptionally scarce. Others prefer to treat it as an extraordinary object whose wider context remains uncertain. Neither position requires exaggeration, and neither removes the central fact that the machine represents an unexpectedly sophisticated combination of astronomy and mechanics. There's also a more imaginative fringe possibility that other devices of comparable complexity remain hidden somewhere beneath Mediterranean soil or water. Perhaps another shipwreck contains fragments. Perhaps an ancient workshop site holds gears that have never been recognized for what they were. Such possibilities are intriguing, but there is currently no reason to assume that a second Antikythera mechanism is waiting to be discovered. The uncertainty is enough. You do not need an underground vault filled with ancient computers. You need one survivor. One machine can demonstrate that a possibility was real. That is why the mechanism matters so much. It changes the question from whether ancient people could build such a device to how they developed the knowledge required to build it, how widely that knowledge circulated, and why so little of the tradition remains visible. Those questions led away from the fantasy of impossible ancient technology and towards something more human. Patience, memory, teaching, craft, curiosity. The mechanism is not evidence that ancient people were secretly modern. It is evidence that they were themselves, working with the materials, mathematics, observations, and institutions available to them, yet capable of astonishing intellectual and practical achievement. That is more interesting than a mystery involving visitors from somewhere else. It means the intelligence was human. The hands were human. The mistakes were human. The calculations were human. And the disappearance was human too. You return once more to the imagined instrument beneath the soft light. Its wooden case is warm. The bronze inside is cool against the darkness. You turn the control gently, and the pointers begin to move. The moon follows its calculated path. The calendar advances. The eclipse cycle unfold. The stars outside continue their distant motion. For a few quiet moments, the machine joins the human world with the celestial one. Then you stop turning. The gears become still. Nothing is lost in that moment. Nothing needs to happen. The machine simply rests. And perhaps that is the most fitting image with which to leave it. Not as a technological miracle, not as proof of a secret civilization, not as an answer to every question, simply as a surviving fragment of a world that knew more than we can completely recover. A world where skilled hands could translate observations of the heavens into bronze. A world where time could be counted, modelled, and turned. A world whose workshops, teachers, calculations, experiments, and unfinished machines have mostly disappeared. You can almost hear the Mediterranean at night. The water moves against the shore. A distant vessel creaks softly. See, the air carries salt and the faint scent of oil from a lamp. Above everything, the moon continues across the darkness. Its motion is ancient. Its cycle is patient. And somewhere beneath the silence of history, a handful of bronze gears still remember how human beings once tried to follow it. Perhaps there were other machines. Perhaps there were other workshops. Perhaps whole traditions disappeared without leaving even a corroded fragment behind. We cannot know, but perhaps that uncertainty is part of the gift. The ancient world does not need to reveal everything before it becomes meaningful. Sometimes a few surviving pieces are enough to show how much has vanished. Sometimes one machine is enough to remind you that history is not a complete record. It's a collection of things that happen to survive. And perhaps, somewhere beneath another layer of earth, another quiet piece of the human story is still waiting. Now let the image of the mechanism become softer. You no longer need to examine every gear or count every tooth. Let the bronze fade gently into shadow. while the small movements of its imagined pointers become slower in your mind outside the ancient room, the night remains calm. The stars continue their patient journeys, requiring no witness and asking nothing from you. You can let the questions remain unanswered. You can let the missing pieces stay missing. There is no need to reconstruct every vanished workshop tonight, or to discover every forgotten name. The past can remain partly hidden. Perhaps that is one of the reasons it continues to draw us toward it, because there is always another quiet corner waiting beyond the edge of what we know. Imagine the sea surrounding Antikythera beneath a dark, peaceful sky. Far below, the ancient wreck rests among stones and drifting sand. The bronze fragments remain still. The currents move gently over them, as they have moved for centuries. You breathe slowly. The room around you grows quieter. The ancient machine no longer needs to turn. Its purpose has already been fulfilled. It has reminded you that human beings have always watched the sky with curiosity, always searched for patterns, and always tried to preserve what they learned. Some knowledge survives in books, some survives in monuments, some survives in machines, and some becomes silence. Tonight you can leave that silence undisturbed. Let the moon continue its quiet journey. Let the stars remain distant. Let the old bronze rest beneath the sea, and as your thoughts grow slower, you can carry only one gentle idea with you. Human history is vast, imperfect, and full of forgotten paths. Somewhere within that darkness, small fragments still wait to be understood. Perhaps the story is not yet complete. Good night.